And sorry for that. And it's my great pleasure and honor to introduce our speaker this morning. It's Professor Bhiksha Raj. So Bhiksha is supposed to put on the second slide.
Yeah.
Yes. So Bhiksha is a professor at Carnegie, the Language Technologies Institute, but he also worked learning the ECE department, technology department, and also more recently the Mohammed bin Zayed University at Abu Dhabi in United Emirates. So what can I tell you about Bhiksha? Is also a fellow of IEEE, and the fact that he works in all these listed affiliations means that he's a top person in speech and audio processing, a top person in machine learning, as you'll have a chance to see today, hopefully, and also in a number of other areas, like, for instance, quantum computing, and an area in which we have been cooperating a lot, which is privacy-preserving machine learning. So Bhiksha started coming to this summer school a couple of years ago.
Many years ago.
And I remember when his course on Introduction to Neural Networks was kind of at closer to the end of the summer school, but then that's the progress in machine learning. It started being sooner and earlier and earlier in the summer school because there was so much stuff to say. But it's always been one of the top ranked courses here in the summer school. We are really privileged to have him here, and I'm especially privileged to have him as a great friend. Yeah, thank you.
Thank you. That was very nice. Thank you for the wonderful introduction, Isabel. Morning, everybody. My lecture today is an introduction to neural networks. What I will not be doing is to teach you about neural networks. What I will be telling you is what it is from a historical perspective and what it can model and what it actually learns. Now, all of us are very familiar with neural networks by this time. They're all over the place, but do we know why they do what they do? So we're going to take a look at that. This is a brief introduction to myself. I am a professor in Carnegie Mellon University. That's a nice picture I found on the web in various departments. I'm currently also visiting at the Mohammed bin Zayed University of AI in UAE. And you can, if you want to get in touch with me for anything, my email is on the slide. The lecture today is permitted to be interactive, meaning if you have any questions at any point, feel free to interrupt. Please do ask. You don't need to hold off everything to the break or until after the lecture. Anyway, let's go through the parts. What is a neural network? Now, neural networks by now we know have become kind of the state of the art in anything related to AI. And they've basically taken over every field that you can think of. And you can trace this history back. All of this is very recent. If you went back to only 2015, nobody was using neural networks for anything serious. And then in 2016, something strange happened. So look at the date over here. This is October 2016. Microsoft showed for the first time that they could build a speech recognition system that outperformed human beings on some tasks. Now, we have been working on speech recognition since the 1950s. It was largely assumed that that computers would likely never catch up with humans. These days, computers do a better job than humans. The first time this happened was in 1916, October. Or machine translation in 2016. In October 2016, if you had used Google Translate, and if you had translated something from English to Spanish, taken the Spanish and translated it back to English, what went in and what came out would not have looked anything remotely similar most of the time. It simply didn't work. And then in November 2016, here it is, there's a date, things suddenly started working. And suddenly we had an online translation service, which was so good that even professional translators would first put whatever they wanted to translate through the system and then make their edits. How did that happen? Well, in both cases, both in Microsoft's case and in the Google Translate case, what happened was there was a switch to neural network-based systems, neural network-based speech recognition, or in this case, neural network-based translation, or other things like image segmentation and image classification. Now, here's a picture that I found on the web. So I can't be entirely sure that this particular picture is authentic, but this is typical of what a neural network can do these days. Given a very complicated picture of this kind, it can identify and segment out every single significant object in the image and tell you what it is. So here, for example, it says that this is a human and the human's carrying a bag. There's a push cart over here. This is a human on a bicycle. The human's carrying a bag. All of these have been segmented out and they're being identified. This was not possible 5 years ago, 7 years ago at this point, but now it's very commonplace. Similarly, computer games. The standard for artificial intelligence was games. For a very long time, we thought that chess was the limit of human intelligence, and that a computer would never actually beat the best grandmasters at chess. Now, this illusion was shattered in the late 80s when researchers at Carnegie Mellon built the first chess AI that beat a grandmaster. And then these same guys went over to IBM and later built an AI that beat the then world champion, Garry Kasparov. And after that, no human champion has ever beaten a chess AI. But then we continue to assume that, yes, maybe chess is too simple. It has only 10 raised to 120 states. Let's go to something more complex like Go, which has 10 raised to 180 states. And here, a computer can never beat humans. And this was the expectation till, you guessed the date, 2016, when for the first time, a neural network-based AI beat the human champion at Go. And of course, these days you have games like AlphaGo. I mean, it's so commonplace that you can literally download it off the web. So it can start from scratch. The game will play itself, and in a few hours become better than any human being that ever played, and better than most of the AIs out there. So it gets better. And again, this is due to neural networks. Or something like this, captioning images. This is something that we just take for granted these days, that you can stick an image into an AI and it's going to describe it for you. But back in 2016, early 2016, this was unimaginable. And then here was the first paper that came out on it. And these are captions. Man in black shirt is playing a guitar. Construction worker in orange safety vest is working on a road. 2 young girls are playing with a Lego toy. Well, one of them is not a young girl, but still, you get the idea. Getting the right thing. Boy doing a backflip on a wakeboard. Girl in pink dress jumping in the air. All of these were automatically generated back in 2016 for the first time. And again, this was thanks to neural networks. And of course, by now, neural networks have practically become the de facto when you speak of AI. We are all familiar with large language models. Something like Stable Diffusion can pretend to be Van Gogh. AlphaFold has decoded almost every protein known to mankind at this point. So neural network-based AI has taken over a variety of problems from biochemistry and medicine, where you can determine protein structure or discover new medicines, from public health and sociology, for predicting epidemics, for analyzing and predicting human behaviors, for driving, self-driving cars, defense. Only recently, the DARPA revealed that they now have F-16s that can fly themselves and outperform human pilots every single time. Speech processing, of course, predicting stock markets. In every case, all of these have been powered by neural networks. So, these things seem to be magical, right? What are these things? We have to find out. But even before that, here's the situation. AI has become so synonymous with neural networks that if you're not familiar with the technology, you're going to be jobless if you want to work in the field. If you want to do anything related to data science, AI, machine learning, anything related to computers, the expectation is that you know what these things are, you know how they work, and you know how to manipulate them. So what are these neural networks? Over the next 3 hours, I'm not going to teach you neural networks, as I mentioned. What I will do is to go back and try to look into it. Where do they come from? What was the original principle? What are their capabilities at a very high meta level? We're going to use very simple toy examples, things that you will not have to strain your mind to think to understand, and try to see how these things sort of come together, and you can sort of imagine how these could scale up into very complex tasks. We'll also look at their limitations and what possible pitfalls there might be. Now, this is not, of course, exhaustive. This is just a sampling. So in all of the cases that we just saw, when we want to understand what a neural network is, here's what happened. We had a box, and things went in and things came out. A voice signal went in, a transcription came out if you were performing speech recognition. An image went in, a caption came out. Or a game state went in, the next predicted game state came out. So there was some box. And what's in these boxes? That is the magic, right? Now, the thing we have to realize that in all of these tasks that we originally began talking about, like transcribing speech, playing games, captioning images, these are essentially human tasks. These are tasks associated. You don't see a dog going out there and captioning an image. So these are powered by our brain. And so maybe to understand how these things happen, the thing to look at is the human brain itself. Or even before that, the process of cognition. How do we cogitate? Now, how do we think? How do we process information in our heads? Now, this, how we process information and how we actually perform our reasoning tasks is a question that people have been asking for thousands of years, not tens, not hundreds, but thousands of years. The earliest work goes back to about 400 BC. So, or the earliest recorded work goes back to about 400 BC. So what are all of these magical capabilities of human beings that we would like to understand? Humans can learn, obviously. We can solve problems. We can recognize patterns. We can create. We can just sit in one place and think and come up with new ideas and thoughts. So this is what we would like to emulate. And to emulate this, we need to know how we do it. So the problem here is that, as Marvin Minsky says, if the brain were simple enough to be understood, we'd be too simple to understand it. But we might as well try. And so the first ideas on the topic go back to Aristotle and Plato, who you can see in this famous painting from the Sistine Chapel, the School of Athens. I think that must be Aristotle. What happened? Amazing. This thing froze. Anyway, so I'm assuming that here is Aristotle, and that's Aristotle, and that's Plato, I think. So they came up with the first ideas of how the brain worked. They call it, this is what we call associationism today. The idea was that humans learn to perform their reasoning tasks through association. So this is the formalism that was prevalent amongst the scientists of the day from 400 BC almost till 1900 AD. This theory lasted for 2,300 years. What is associationism? Very simple. That we form associations between percepts through observation. So for example, every time you see a lightning, a little while later, you hear thunder. So you form an association between lightning and thunder. And now that the association is formed in your head, if you see a flash of lightning, you will expect to hear thunder. It's a prediction that you have made forwards. On the other hand, if you hear thunder, you will assume that a lightning has struck someplace. There's an inference that you have made backwards. So all of these are formed through associations. And this is actually a very nice theory that we actually still use. Every time you use a neural network, every time you use a machine learning algorithm, every time you do anything at all with prediction and inference, you are actually using a mathematical form of associations. So the concept is very solid, but it doesn't explain everything. Sure, we base everything off associations, but where are these associations stored? How does a human do it? And so this clip is not working. Now, clearly, these things must be stored in the brain because that's where everything is happening. And what is the brain? What does the brain look like? By the mid 1800s, microscopy had gotten to be good enough that we knew the structure of the brain in great detail. We knew that it was a giant mass of interconnected cells that later came to be called the neurons, and that all of these connected to one another. So somewhere, all of this ability to form inferences must be hidden somewhere in this structure. So what does the network and brain look like? It's got lots and lots of neurons. Each neuron has incoming connections from many neurons. Each neuron connects out to many neurons. This is what we knew. So the next step is to figure out how all of this translates to being able to perform the kind of inferences that we do perform. And the first idea for this came from this guy, a fellow called Alexander Bain, who was a philosopher, a mathematician, a logician, a linguist, a professor back in the 1800s. When you became a scientist, you were pretty much everything. And so he was one of those polymaths. And in 1873, he came up with the first theory. He said that all of the power of the brain lies in the connections, the manner in which things connect to one another. So believe it or not, the first theory of neural networks and what we call artificial neural networks these days goes back to 1873. In fact, Alex Bain also came up with computational models of these networks. So here is an example where he showed that the same network can have different outputs for different inputs. Now, this is something that we just take for granted. It's obvious. In 1873, it was not. So in this network, you can see that if you assume that each circle represents a neuron that will fire if it has two inputs, then if A and B are turned on, X will fire. If B and C are turned on, Y will fire. If A and C are turned on, Z will fire. So the same network is going to have different outputs based on the specific pattern of inputs. Or here's a network where the output depends on the strength of the input. If the input is weak, only Y will fire. If the input is strong, both X and Y will fire. So Alex Bain actually came up with this idea of networks, where just based on how things were connected, it would respond differently to different stimuli, which he said would actually explains how the brain works. And he also came up with ideas of how these connections can be learned. So he said when two impressions concur or closely succeed one another, the nerve currents find some bridge or place of continuity, better or worse, according to the abundance of nerve matter available for the transition. So it's a lot of words, but basically predicts what was later known as Hebbian learning. So he came up with a theory that you could actually put math to and write a mathematical model for it. This was back in 1873, right? So just think about it. So why did things get stuck if the first artificial neural network was proposed in 1873? Because people doubted. The idea that the same net can have different outputs for different inputs, something that we just take for granted, was not back then. And so as Bertrand Russell says, the fundamental cause of the trouble is that in the modern world, the stupid are cocksure and the intelligent are full of doubt. Bain was full of doubt. And so in 1873, he postulated that there must be 1 million neurons and about 5 billion connections to acquire 200,000 concepts, what he called percepts. Then by 1883, 10 years later, he sort of got concerned that he hadn't taken into account the number of partially formed associations, things that were still being developed by the brain. If you also wanted to store those, you needed a lot more networks and a lot more neurons and a lot more connections. And another 20 years later, he just recanted all his ideas. He said that the brain is too small. I mean, we cannot be explaining everything that the brain does simply on the basis of connections and of how many neurons it has in the connections, because it doesn't have a sufficient number of neurons and connections. The problem is that he had grossly underestimated the complexity of the brain. We have about 80 billion neurons in our little head, and those 80 billion neurons have a total of 100 trillion connections, which is more than enough for the capacity for everything that we do, clearly. And in fact, the largest modern networks, neural networks and models don't even begin to approach this complexity in terms of size. And so this idea that intelligence and the capacity to perform computation is stored in the connections is what we call connectionism. And this concept of connectionism, which was first proposed by Bain in 1873 and restated by David Ferrier in 1876, lives on. Neurons connect to other neurons, and the processing capacity of the brain is a function of these connections. And so modern connectionist architectures, computational connectionist architectures, emulate this connectionist nature of the brain itself. So these are what we call connectionist machines. Your neural networks are connectionist machines. These are networks of processing elements, and all world knowledge is stored in the connection between the elements, the manner in which these things connect to one another. Now, how does a connectionist machine differ from your standard computing architecture? So you must all have, at least some of you have taken computer architecture, right? And so, when I speak of a von Neumann machine, you know what I'm talking about. So what is a standard, what is the architecture of the processor that you have in your phone or in your laptop? It's something like the figure to the left. You have a processor which is separate from the memory, and the memory stores the programs and the data, and the processor draws the program from the memory and the data and does whatever it must, which is why the same CPU can be used to perform so many different tasks. All you have to do is to change what's in memory, and it's got a new program to work on, new data to work on, which is why your small smartphone is so versatile. The problem with connectionist architectures is that it's not like that. You don't separate the memory and the program from the processor. The processor is the program, because the connections between the units is what determines how the processor operates. And so that's why even today, if you want to implement a neural network, you don't actually go ahead and construct a neural network, because when the processor is the program, if you want to change the program, you have to change the processor. You'd have to build an entirely neural network from scratch in silicon if you wanted to implement the connectionist architecture as is. Instead, what we do is to emulate the connectionist architecture in a von Neumann machine. You use your standard CPU or your standard GPU, and you just change the program, right? So as a quick recap of everything that we've seen so far, neural network-based AI has taken over most AI tasks. They originally began as computational models of the brain, or more generally as models of cognition. The earliest model of cognition was associationism. The more recent model of the brain is connectionist. Neurons connect to neurons, and the workings of the brains are encoded in these connections. And current neural network models are connectionist machines. I'll take a pause here for a few seconds in case anybody has any questions, then I'll move on. Any questions? No. Yes. So are you speaking of the brain, or are you speaking of the... Oh. So the human brain, there are various theories to it. We are born, we actually form these, and something that I won't get into. So the brain is actually born as a mess of neurons, and one of two things happens. You either lose connections that exist, or you form connections based on which neurons sort of fire together. We'll go over that briefly in a few seconds. And so there are actually biological processes that decide which connections get strengthened and which connections get weakened. I mean, I could go into that in great detail, but it'll take a little time. But that's at the high level. Maybe we'll see that in a few seconds. Any other questions? Okay, let me continue, right? So here's what connectionist machines look like. They're a network of processing elements. All world knowledge is stored in the connections between the elements. And in fact, one of the earliest models for connectionist machines was by Alan Turing, who basically invented all of computing, although we don't use his designs anymore. So connectionist machines are, the idea is simple, that these basic units themselves are very simple, same as in the brain. All world knowledge is stored in how the units connect to one another. But that doesn't explain everything, right? The units must have some magical property that allows them to be connected in this manner so that they can learn to do everything. So what do these units look like? For that, we'll go back to the brain again. Now, here's what a neuron looks like in your brain or anywhere in your body. It's got this head, which is called the soma. It has lots of incoming connections into the head, the dendrites, through which the neuron connects to other neurons. Every time one of the connecting neuron fires, that signal is transmitted into this neuron. So through the dendritic connection. So when the accumulated excitation from all of the connected neurons exceeds a threshold, then this neuron is going to fire. And that fired signal is going to go down this long leg called the axon to downstream neurons. That's the basic structure of the neuron itself. And then something that doesn't actually relate to artificial neural networks is this little pink sheath that is shown on the picture. That's made of fat. It's called the myelin sheath. And it turns out that how smart you are, it doesn't depend on how many neurons you have in your head. It depends on how much fat you have in your head, because they protect your neurons. And in fact, they actually did some study on Einstein's brain, which they did store. And they found that he didn't have more neurons than more than normal people. He just had more fat in his head. So if you're a fat head, you're a genius, right? Anyways, so we're going to come up with a model which sort of emulates this. And the first people to come up with this model were these two guys, Warren McCullough and Walter Pitts. This was a paper titled A Logical Calculus of the Ideas Immanent in Nervous Activity in the Bulletin of Mathematical Biophysics back in 1943. When this paper was published, Pitts had not yet gone to college. He never went to college. He just dropped out of school at the age of 15. And he was 20 years old when he published this work. So this was what we call threshold logic. Wait. Here they are, right? McCullough and Pitts. Now, again, McCullough was a senior. I like to tell, I already sort of told you what Pitts, who Pitts was, but the story is that Walter Pitts just ended up at McCullough's door as a hobo. He was a homeless guy. And McCullough let him stay. And they worked out the math for the neuron. So if I told you a homeless person went into somebody else's home and I asked you which was the professor and which was the homeless guy, you'd probably pick them wrong, right? Anyway, so here's the model that they came up with for the neuron. That the neuron, each neuron has a bunch of different inputs coming in. Each input has associated with it a weight to the connection. And the neuron itself senses the accumulated inputs from all of its incoming signals. And it's going to respond to this accumulated input. If this accumulated input sort of exceeds the threshold, it's going to fire. So the output becomes 1. If it's less than the threshold, the output stays 0. So they actually came up, because you're trying to model biological connections, and biological connections, you have things that are and things that aren't. You can't have negative things. At least that was the theory at that time. So how do you actually account for negation? So they came up with two different kinds of connections. One was what they called an excitatory synapse, where any signal that went in through the excitatory synapse excited the neuron. Then they came up with something called an inhibitory synapse. Any signal that came down an inhibitory synapse suppressed activation at the neuron. And so using just these two kinds of connections, they showed how a mathematical model for the neuron could perform any kind of Boolean operation. So here, for example, this neuron over here, in each case in these pictures, the neuron will fire if there are at least 2 incoming connections. So here, this neuron gets 2 incoming connections every time. Neuron 2 gets 2 incoming signals every time neuron 1 fires, but 1 time instant later. So this is a delay. This one here If either neuron 1 or neuron 2 fires, then the neuron is going to get two connections, two incoming signals. So this is 1 or 2. Here, each of them has only one incoming connection. So both 1 and 2 must fire for the neuron itself to fire. So neuron 3 in this case is 1 and 2. And here is the case of inhibition. If 1 fires, 3 will fire unless 2 fires. So the circle shows an inhibitory connection. And so if 2 fires, it's going to prevent the neuron from firing. So that's a negation. So this becomes 1 and not 2. So they showed, Pitts and McCullough showed that by constructing things in this manner, you could construct pretty much any Boolean machine. And then they went on to make claims, all kinds of claims about their machinery, including that it could model any Turing machine, which was possibly true. But they couldn't tell you how these connections were learned in the brain. So we have all of these capabilities for the neurons, but clearly for the neuron to perform any particular operation, those connections must be formed. How are those connections formed? So that should answer so to answer that question, we had to wait for this guy called Donald Hebb. He came up with the first theory, where in this book called Organization of Behavior in 1949, which is 6 years after McCullough and Pitts. And his theory stated in simple words said that neurons that fire together wire together. So how does that work from a biological perspective? When two neurons connect to one another, it doesn't mean that the neurons actually touch one another. What it means is that one neuron has a connection which comes very close to the other one. There's a little gap between the two. And the connection over here is through this thing over here, which is called the synaptic head, I believe, which is full of chemicals. And every time the neuron connecting fires, chemicals are released from here, and it makes the neuron underneath also fire. And now each time, but it's not just one connection, right? All of these are very complicated connections. So if this guy fires and succeeds as a result in making this lower neuron also fire, then there's a success, then immediately this head gets a little larger. So the next time the upper neuron fires, there are more chemicals, and so the lower one is more likely to fire. And so the connection gets stronger. You can actually put some math to it. The connection has some weight Wi. If the input is X and the output is Y, each time an X equals 1 results in a Y equals 1, you want the weight to increase. And so you can say W equals W plus eta times XY. So there's a mathematical model for this learning mechanism, what we call Hebbian learning, to answer the question that we just had. And so this is how these connections are formed. Now, this model is still very valid, and it's used a whole lot in machine learning. The only issue over here was that the manner in which this was stated, the weights could get larger, but they couldn't get smaller. Eta was always positive, right? So in that case, can you see what issue might arise in a situation like this? Anyone? The networks always, the weights always get larger. They don't get smaller. So in the limit, if I give you a finite, all of the neurons, all of the weights are going to keep getting larger and larger, and they will saturate. Eventually, the network is going to become meaningless, right? So you need things to increase and also decrease. So a better model was put forth by this guy, Frank Rosenblatt, in the 50s. He was a psychologist and a logician at Yale, and he's the inventor of the perceptron, the model that we still use, that was in 1958. So here's the simplified mathematical model for his basic perceptron unit. Now I'm calling it the basic unit because this was not the actual unit that he defined. We'll get to that in a minute. But this is still very much like the model that we just saw from Pitts and McCullough, in that the neuron is supposed to has many inputs. Each input has a weight associated with it. And so the total input that the neuron receives is a weighted sum of all of its inputs. And if this weighted sum exceeds some threshold minus b, then the output of the neuron is going to be 1. Otherwise, the output remains 0. So this is what the electrical engineers will know as threshold logic. Now, Rosenblatt's original perceptron was this very complicated structure. It was actually a multi-layer perceptron. So his idea was that the retina has many sensors, and that you have different combinations of these sensors going into the next layer of the network, and that they are downstream processes that work on these outputs, but then that which also feed back, and so the whole model was pretty complex. But then if you look at any one single unit here, that single unit looks like this. It has a weighted, it looks at it computes a weighted combination of inputs and fires if that exceeds a threshold. Now, what Rosenblatt showed back in the day was that a structure like this could learn basically any Boolean function. And so this led to all kinds of exaggeration, like this one from the New York Times. The embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. In 1958, Frankenstein monster designed by the Navy that thinks, 1958. That's because the Navy funded this research. Now, clearly, this little structure fell way short all of this exaggeration, and so largely thanks to overhype, funding stopped because the output didn't match the hype, and research in neural networks sort of basically went dry for almost 20 years before people began poking with it again. We had to wait another 60 years before things actually became functional. But then, anyway, going back, here is the learning mechanism that Rosenblatt actually gave us, which was a small variation on Hebb's rule, and it was this. He said that the weight of any connection is going to change. Remember Donald Hebb's rule. Donald Hebb's rule said that if X fires and results in Y firing, then the weight is going to increase in proportion to X times Y. But is that always the case? The problem there was that if Y was already doing what it had to do, you were unnecessarily making a weight larger. So Rosenblatt's idea was that if you only correct if Y is currently making a mistake. If you want Y to increase, then you increase the weight, otherwise you don't. If you want Y to decrease, you decrease the weight. And so he defined an error, which is the output between the desired output, the difference between the desired output and the actual output. And the amount by which the weight changed was proportional to this error. This was Rosenblatt's learning rule. Now, here you'll notice something different from Hebb's learning rule, in that there's a D of X, which indicates a desired output. Whereas Hebb's learning rule basically said, if I start with a brain and just let things fire, how do things connect to themselves? And Rosenblatt actually proved that this is a very nice algorithm, which will where if you have some inputs and some target outputs, if you apply this algorithm repeatedly, then under some conditions, the neuron will actually learn the relationship. Now, more importantly, the basic perceptron itself, the basic unit itself that we later came to call the perceptron. Again, just to clarify, this was Rosenblatt's perceptron. This was just one unit in his big structure. But in modern nomenclature, this is what we call the perceptron. Nobody thinks of this figure here. So every time I speak of a perceptron, I'm just speaking of this one unit, which is basically one dot in this plane. So that one unit by itself is actually pretty powerful. So this is a unit where it receives a bunch of inputs, and it considers a weighted sum of the inputs and fires if the weighted sum exceeds a threshold. So here you can see these are different examples. The threshold is shown in the circle. The weights of the connections are shown above the arrows. Here the threshold is 2. Only if X and Y are both 1 will this neuron fire. So this is X and Y, right? Here the threshold is 0, but the weight is negative. So if X is 1, the total input is going to be negative and it will not fire. But if X is 0, the total input is 0 and it will fire. So this is a negation, right? This guy here, if either X or Y are 1, the total input is going to be 1, it will fire. So it's X or Y. And so you can show that this basic unit can emulate any Boolean function. Any Boolean function? Not quite, right? It cannot emulate an XOR. So here, for example, there's no way for me to set any pattern of weights for the two inputs and or any threshold such that the output is X XORed with Y. Now, if you want to actually compute the XOR, then you're going to need more than one of these units that are connected together. And so, going back, what Rosenblatt himself knew, and Brofminski and Papert also later sort of showed, was that these individual units that we are speaking of as the perceptron are very powerful, but they're not infinitely powerful. They're weak computational elements. If you want to compute more complex operations, like even say the XOR, then you have to network these guys. But once you begin thinking of networking, more complex functions become possible. So here's the XOR, right? So in this case, now I have three perceptrons. The first perceptron computes X or Y. The second perceptron computes not X or not Y. And the third perceptron simply ORs these two guys. And once I do that, the output of this three perceptron structure is an XOR. And here it's useful for us to introduce some terminology. These perceptrons in the middle, these are what we will call the hidden layer, because you don't really need to see their individual outputs. You're only interested in the output over here to know that it's an XOR, right? And so we find that once we begin connecting these basic units together, we can compute other Boolean functions. In fact, we can compute arbitrarily complex Boolean functions. So for example, here is a network of a bunch of perceptrons, and it computes this crazy function on top of the 4 inputs. And so I can compute, if you give me a Boolean function, I can always construct a network of perceptrons that will compute the Boolean function. And so the story so far, continuing what we've seen so far, neural networks which began as computational models of the brain are connectionist machines. The McCullough and Pitts model modeled neurons as Boolean threshold units. And Hebb's learning rule gave us a way for learning the weights, but it didn't quite work because it was unstable. Then we had Rosenblatt's basic perceptron, which is a variant of the McCullough and Pitt neuron with a provably convergent learning rule. But the individual units are limited in their capacity. For example, they cannot model an XOR. But once you begin networking them, you can model arbitrarily complex Boolean functions. So, questions? Any questions? All right. So let me continue from here, right? I'm talking about Boolean functions. Everything I've spoken so far was about Boolean functions. Inputs are zeros or ones, the outputs are zeros and ones. But then our brain is not Boolean. Our brain is working on continuous valued inputs. We are seeing real things. We are listening to real things. We are responding in real ways, right? So we have real inputs and we make non-Boolean inferences and predictions. So how can we sort of correlate these two ideas? Let's go back and look at the perceptron again. Now, it's still the same model, but x1 through xn are no longer Boolean inputs. x1 through xn are real valued inputs. The weights w1 through wn are also real valued, and the unit fires if the weighted sum of the inputs exceeds a threshold. So, once you write it this way, then you can actually sort of redraw the figure. You can redraw the perceptron as a combination of two structures. The first structure simply computes a weighted sum of the inputs. The second structure, which we will call, and so there's a weighted sum term that comes in here. The second component compares this sum to a threshold. It outputs a 1 if the sum exceeds a threshold, and it outputs a 0 otherwise. This is what we call the activation. And once you separate these two components, you can actually change this function in here inside this little box to something different, like say a sigmoid, in which case you can think of this output as a probability of firing rather than actually firing. Anyway, I'm going to continue thinking about it in terms of this threshold activation, where the neuron fires if the weighted sum exceeds a threshold. So now let's consider a simple example where where I have a perceptron with only 2 inputs. If I have 2 inputs, x1 and x2, then the output is going to be 1 if the weighted sum of the inputs exceeds a threshold and 0 otherwise. So where's the boundary? The boundary is where the weighted sum is exactly equal to a threshold. That's going to be, in the two-dimensional case, it's going to be a line, right? And so the output is going to be a 1 on one side of the line and a 0 on the other side of the line. So if I plotted this whole thing in 3D with the z-axis showing the output of the function, then it's going to look like the step function over here. There's a plane. On one side of the plane, the output is 0. On the other side, the output is 1. So this can generalize to higher dimensions as well. Now, once you see what the perceptron is doing, you can see why it can compute Boolean functions. In a Boolean function, the output is either 1 or 0. Now, if I compose a perceptron of this kind, where the line goes like so, then if I have two inputs, these are the four possible input combinations, right? 0, 0, 0, 1, 1, 0, and 1, 1. And if this is my boundary, then you can see why the output is 1 whenever any of the inputs is 1. And so now this becomes an OR. On the other hand, if I move the boundary out to this place, you can see that it only fires when both inputs are 1. So this becomes an AND. And if I change the boundary to be like this, it becomes a negation. So you can see what kinds of Boolean functions you can actually compute. Once you see this, right, we've seen how it can compute Boolean functions, but then you can see it's easy to sort of conceptualize that you can learn decision boundaries of any kind. For example, let's say I still have two-dimensional inputs, but I want to construct a network. And now I'm not speaking of individual neurons, I'm speaking of networks of neurons. And I want to construct a network that outputs a 1 if the input is in the yellow region and a 0 otherwise. How can I use units of this kind, which have a simple linear boundary and a 1 on one side and a 0 on the other side, to compose this decision boundary? Some of you have probably already seen the answer. So here's what I can do. I can have one neuron which outputs a 1 if the input is above the horizontal line and a 0 if the input is below the horizontal line. I can have another neuron which outputs a 1 if the input is to the left of this angular line and 0 otherwise, right? A third neuron captures this decision boundary. It outputs a 1 below the line and a 0 above. Here's the fourth neuron, which captures this boundary. The fifth neuron captures this boundary. And so now I have one neuron for every one of the boundaries. And then I can have a final neuron which simply ANDs all 5 of them. It's going to sum the outputs of all 5 neurons, and it's going to compare this sum to a threshold 5. And if the sum is 5, it means that all 5 of them have fired. All 5 of them will only fire inside the pentagon. And so now I have composed a network that can compute this pentagonal decision boundary. Very easy, right? But once I do that, I can actually compose more complex decision boundaries, like this double pentagon. What do? I have one subnetwork which fires if the input is inside the first pentagon. I have another subnet which fires if the input is inside the second pentagon. And then I finally OR those two outputs. This means that the network is going to become output of 1 if the input is in either of these two yellow regions and a 0 otherwise. But once you see that you can actually compose this double pentagon region, you can compose arbitrarily complicated decision boundaries, right? How would you do this? You can just take this complicated decision boundary. I can sort of separate it out into little polytopes and compose any decision boundary that I want. And so when I'm performing classification, for example, if I'm looking at pictures and deciding if this is the digit 2, if I think of it in terms of digitized inputs like you get in your images. If you were looking at images of MNIST digits, they are 784 pixels. So you're looking at 784 dimensional inputs. In that 784 dimensional space, there is some region shown by this peanut over here, in which all the instances of 2 lie. And so all you need to do is to compose a neural network that outputs a 1 if the input is inside the peanut and 0 outside. And you can see how this can be done, right? And so just extending to what we saw, extending what we saw so far, we saw that MLPs, multi-layer perceptrons, and so I'm introducing a terminology over here, networks of perceptrons, which are connected to one another as opposed to individual perceptrons. They're computational models. Individual perceptrons are computational equivalents of neurons, and the MLP is a layered composition of many perceptrons. They can model Boolean functions. They can model each individual perceptron can act as a Boolean gate. And so networks of perceptrons can model any Boolean function. They're Boolean machines. Each of these perceptrons represents a function over a linear, they represent Boolean functions of Okay, I'll speak on to this. Can you hear me? Fine. Working? Perfect. You can have all the AI in the world. Anyway, so you get an idea of how these simple, what are these basic units? Our story was we wanted to model intelligence. We thought we were going to model it by modeling the brain. We looked into the brain and we saw that it was a connection of basic units. So we decided to construct networks of basic units. We modeled the individual unit itself. We found the individual unit captures a linear boundary, but that was enough to capture or represent all kinds of Boolean gates. And then once you began composing those together, you could compose any Boolean function, and you could go one step ahead and you could compose any classification boundary at all. So that's all very fine at an abstract level, right? But what does the perceptron really model? Is there a semantic interpretation? For that, let's go back and look at the individual perceptron itself. Here is the individual perceptron. Again, the individual perceptron looks at a weighted sum of inputs. It outputs a 1 if this weighted sum exceeds a threshold, and a 0 otherwise. So if I wrote all of these weights down as a vector W, all of the inputs as a vector X, then it's going to fire if the inner product between X and W exceeds a threshold. Now, let's take a look at this again, right? What is the inner product between two vectors? The inner product between two vectors, math tells us, is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between the two. Now, here's a very strange fact. In high dimensional space, all vectors are the same length. That's because if you think of a high dimensional space, as you increase the dimensionality of the space, as if you take any sphere, most of the volume of the sphere ends up near the surface. When you get into thousands of dimensions, basically the entire volume of the sphere is within a very infinitesimally thin region of the surface, which means if I just drew random vectors of 1,000-dimensional vectors, all of these vectors are going to be kind of the same length. So what this means is that if I'm considering the inner product between two vectors, this is basically a function of one and only one thing, which is the angle between the two vectors. So what we are saying is that this perceptron fires if cos theta between the two vectors is greater than some threshold. Or in other words, if the angle between the two vectors is less than some threshold. And so, more explicitly, anytime when I'm looking at a neuron, it will fire the weights themselves represent a pattern that the neuron is looking for. So for example, if I wanted to compose a single perceptron which looked at these LED patterns to decide if it was the number 2 or not, then the perceptron's weights your best bet is to set the perceptron's weight in the shape of 2. So if you compute the inner product between the inputs and the weights, that inner product is simply going to be the correlation between the two, the input and the weights. And if that exceeds the threshold, If it falls below a threshold, the two are not similar. You can say it didn't fire. If it exceeds a threshold, you can say it fired. So because you can say you found a match, and the unit can fire. So individual perceptrons are correlation filters. And so when you begin composing networks of these basic units, you're basically composing correlation filters on top of correlation filters. The first layer over here is going to be, or not the input layer, but the first layer after the input is going to be a bunch of feature detectors, which detects if certain features have happened in the input or not. The weights of these neurons are going to show you what features they are trying to detect. And then the next subsequent layers are going to sort of compose patterns from these detectors. So for example, if you were trying to build a network which looked at these old LCD grids to determine if the grid represented a valid digit or not, then you would expect that the first layer neurons are going to detect the kinds of patterns that you would expect to see clearly in digits, or the kinds of patterns whose presence clearly indicates that this is not a digit. The rest are irrelevant, right? And then the next layer might, for example, just compose these together and say that this guy could detect based on the features detected by the first layer neurons if the digit 1 has happened. This guy could detect if the digit 2 has happened, and so on. And so then the final structure just decides if any of these patterns have been found. But again, the point over here is that if you take away the abstraction, each neuron is basically looking for specific patterns, and the specific pattern that it is looking for can be determined by direct inspection of the weights itself. On the other hand, but this works best at the layer closest to the input. And then as you go deeper into the network, it's going to become harder and harder to interpret. And so, continuing, MLPs are perceptrons are correlation filters, which is what we just saw. And multi-layer perceptrons can be thought of as Boolean formulae over patterns detected by perceptrons. So here, for example, these are the patterns detected by the perceptrons. And then this guy can say, if this and this, but not this, 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 or this, it's a 1, right? So the next subsequent components of the network are basically Boolean functions over the basic pattern detectors, and these can be hierarchical. And finally, if you look at MLPs in terms of classification, the network fires if the combination of detected basic features matches an acceptable pattern for the desired class of signal. Like in the case of the digits, if you found the right components of the digits, or if you are trying to build a face detector, if your the basic feature detector detected all the features that you'd associate with a face. Now, again, we've looked at MLPs as Boolean functions. We've looked at MLPs as classifiers. But what about as real valued functions? MLPs can compose any Boolean function. They can compose any classification boundary. Can they also compose any real valued function? And the answer is yes. So here is a simple MLP. I have 2 threshold gates, threshold perceptrons. The first one fires if the weighted in this case, there's just a single input and a single output. And so this first one fires if the input exceeds a threshold T1. The second one fires if the input exceeds a threshold T2. And each of those 2 outputs are added again with weights 1 and -1. Now look at how this little unit behaves as the input varies from -infinity to +infinity. Until the input becomes T1, there is no input, so the output is going to be 0. When the input exceeds T1, but it's less than T2, then one of them is going to become 1, the other is 0, so the overall output of the network is going to become 1. When the input exceeds T2, both of these neurons will fire and they'll cancel each other out. And so now the output goes back to 0. So this little network has an output of 1 between T1 and T2 and 0 elsewhere. Once you can compose that, you can compose any function, right, to arbitrary precision. So if I have this crazy blue-shaped function, I can compose the blue shape function by taking many of these little steps, scaling them to different heights and adding them together. And so this means that I can compose an arbitrary real valued function of at least in the case of a unidimensional input. Now, this composition is not going to be exact. It's an approximation. I can make the approximation arbitrarily precise, which is why neural networks are called universal approximators. They're not called universal functions. They're called universal approximators. You give me the function, I can approximate it to arbitrary precision. And so we saw, in addition to what we've just seen so far, that MLPs are connectionist computational models, and they are classification engines which can identify classes in the data, where individual perceptrons are feature detectors, and the network fires of the combination of detected basic features matches acceptable patterns. MLPs can also model continuous valued functions. So that's the basic idea of what these things are. We'll look at limitations and what is this business of depth in a few minutes. But if you have any questions, I'll take them. Questions, anyone? No. Okay. So for a quick recap, so here's what the perceptron was again. It saw a weighted combination of inputs and fired if this weighted combination exceeded a threshold, right? Alternately, I can say that it's looking at an affine combination of inputs. Now, what's the difference between affine and just a weighted sum? If I'm looking at a weighted sum, you're just looking at summation wi(xi). When I think of an affine combination, it's going to be summation wi(xi) plus some bias. And if the bias is minus t, then this is like saying I'm looking at an affine combination of inputs. Z equals summation wi(xi) minus t. So that's this term z, which then gets put through a threshold function. This threshold function is going to output a 1 if z is positive and 0 otherwise, right? This is your basic perceptron. Now, again, to recall, if I redraw the figure like this, then I can actually put z through something other than a threshold function, like a sigmoid, and I can get continuous valued outputs. So what's inside this box is what we'll call the activation. It's the function that acts on the affine combination of inputs and produces an output. And once you figure that, you can actually take this perceptron and separate it out into two components. The first component computes the affine combination of inputs. The second component applies a function to it. Then you can put in other functions there, not just the threshold, not just the sigmoid. You can have something like a tanh, or these other functions that you might have encountered, the ReLU, the soft plus, and so on, and get different kinds of outputs. But for now, I'm going to continue to assume that this box has a threshold function of this kind, because a threshold function is what makes explanations most simple and provides the most intuitive understanding of what's going on, right? So we also sort of briefly introduced the notion of a multi-layer perceptron. A multi-layer perceptron is a network of perceptrons, many perceptrons connected in layers. But when I use this term, I'm being very casual, right? I introduced a term, a layer. What is a layer? So also, when we began speaking of the networks, we spoke of deep networks. What is a deep network? So let's go back and look at some definitions. What's a layer and what's a deep network? First, let's introduce the notion of depth. The notion of depth comes from graphs. Now, in any directed network of computational elements with source nodes, input source nodes and output sink nodes, then depth is the length of the longest path from source to sink. Now, a source node is a node that has only outgoing edges. All edges have directions. A sink node is one that has only incoming edges. And so over here, I have one source node, I have one sink node. And in this figure, there's a path of length 1 and a path of length 2 in this left graph. The depth of this graph is 2 because the length of the longest path is 2. Here, I have 4 nodes There's one source node, one sink node. It has a path of length 1, path of length 2, and another of length 3. The depth of this graph is 3 because the longest path is length 3, right? So now, having defined that, what is a layer? Look at this picture over here. And this picture, there's something unique about all these red boxes, red circles. What is that? Anyone want to tell me? Pardon me? They're all at the same depth, right? All 4 red circles are the same depth with respect to the input. Similarly, what about the green ones? They're all the same depth with respect to the input, right? So the 4 red neurons represent the first layer. It's the set of neurons which are at depth 1 with respect to the input. The green neurons represent the second layer, the set of neurons which are at depth 2 with respect to the input. The yellow neurons are the third layer. They're at depth 3 with respect to the input. Don't get confused by the odd arrangement in the picture. Depth has a formal definition, right? Now, and so layer, the definition of a layer is also very formal. Now, once we know what a layer is, we can look at the notion of the depth of a network itself. This network has 4 layers. So it has the input. Actually, it has 3 layers. This is the input. 1 layer, 2 layer, 3 layers. On the other hand, this network, if this is the input, has only 2 layers. And this network over here has 1, 2, 3, 4 layers, right? It has a depth 4, meaning the longest path from input to output over here is 3. For here it's 2, here it's 4. Any network where the depth of the network is greater than 2 is called a deep network. So this network over here is not deep. The depth of the network is only 2. This network is deep. The depth of the network is 3. This network is deep. The depth of the network is 4. So there's a formal definition of depth of a deep network. But we don't need to get hung up on the formal definition of a deep network, because the actual kind of deep networks that you'll be working with will have many more than 3 layers. They can go up to hundreds of layers. So we kind of know what a multi-layer perceptron is. We know what layers are. We know what depth is, right? So the multi-layer perceptron is this layered network of basic units or perceptrons, where the inputs can be real or Boolean stimuli. The outputs can be real or Boolean. Now, in the examples that I showed you, everything just had a single output, but the network can also have multiple outputs. Now, what can this network compute? What kind of input-output relationships can it model? We've already seen that. We saw that it can compute any Boolean function, any classification boundary, any real-valued function. But what are the limitations? And how does that relate to depth? So for that, let's go back and look at Boolean functions, right? MLPs can compose Boolean functions. They can compose real-valued functions. They can compute classification boundaries. What are the limitations? First, let's look at Boolean functions. We saw that the individual perceptron can represent any Boolean gate, an AND, an OR, or a NOT in this example, right? But then actually individual perceptrons are a lot more complicated, a lot more powerful than that. So here, for example, is a perceptron that takes an N inputs and will only fire if all of the first L inputs are 1 and all of the remaining inputs are 0. If any one of the inputs is flipped with respect to that pattern, then the perceptron will not fire. So you can see how. These first L inputs have weight 1. The remaining inputs have weight -1, right? So the threshold is L. Now, if all of the first L neurons have weight 1, and all of the if all of the first L inputs are 1, and all of the remaining inputs are 0, then the total input is going to be exactly L, because these are going to contribute L, and these are going to contribute 0, right? If any one of these is flipped, so if any one of these guys becomes 0, then the input is going to become less than L. If any one of these guys becomes a 1, because the corresponding weight is negative, the input is going to become less than L. And so this unit will fire only if the first L inputs are 1 and the remaining inputs are all 0. So it's now, here's something a little crazier, right? If I can, in this perceptron, this will fire if any one of the first L inputs is 1, or if any one of the remaining inputs is 0. So this again, this is actually just the same. This is just a variation of this guy, right? If you think about it. So what is the one condition under which it will not fire? If all of the first inputs are 1 and all of the are 0 and all of the remaining inputs are 1. And so you can construct a perceptron which fires under the one negated condition and flip it. So that's but it looks a lot more, superficially it looks a little more complex than that. But the point is that a single perceptron can compute fairly complex functions. Now these things can also be done by Boolean gates, but here's something that cannot be done by a Boolean gate. This is a perceptron that will fire if the total number of inputs is k or more. This is what is called a majority gate. So this can be done by a single perceptron. But if you want to compose the same thing using Boolean gates, that network is going to be exponentially large in the number of inputs. So a perceptron, a very simple perceptron, can compute functions that would require exponentially large Boolean circuits. So perceptron is a lot more powerful than Boolean gates. And yet, in spite of its capacity, a perceptron cannot compute an XOR. We already know this, right? But if we connect up perceptrons as a network, suddenly they can also compute XORs or more complex Boolean functions. So which means that multi-layer perceptrons, networks of perceptrons are universal Boolean functions because they can compute pretty much any Boolean function. Give me a Boolean function and I'll design an MLP that can compute it. But then, if MLPs are universal Boolean functions, for any function over any number of inputs and with any number of outputs, I can always compose an MLP that computes that particular function. But how many layers will that network need? So here in this example, I have this crazy Boolean function on top, and this network has 3 layers, 2 hidden layers and 1 output layer, right? So can I do this whole thing with just 1 hidden layer? Can anybody guess? How would I do this with just 1 hidden layer? Anyone? Since everybody is quiet, I'll give you a second to think about it. Okay, let me give you the answer because it's too early in the morning. Anyway, so here is what is a Boolean function? A Boolean function is just a truth table, correct? The inputs are Boolean, they're all zeros and ones. So I can explicitly list every combination of inputs and the corresponding output. So, and I don't even need to list every combination of inputs. I only need to list the combinations of inputs for which the output is 1. So in this case, I have a Boolean function which is going to output a 1 only for these 6 combinations of inputs. For all other combinations, it's going to output a 0. So this function says that the output will be a 1 if x1 is 0, x2 is 0, x3 is 1, x4 is 1, and x5 is 1. Or if x1 is 0, x2 is 1, x3 is 0, x4 is 1, and x5 is 1. It has 6 conditions under which the output is going to be a 1. Under every other condition, the output is going to be a 0. So I can write this as a n disjunctive normal form. And the DNF form is going to have 6 clauses. Each clause represents 1 row in the table. So this first row says that the output is going to be a 1 if x1 is 0, which is to say not x1, x2 is 0, which is to say not x2, x3, x4, and if x5 is 0, right? The second clause over here captures the second line, not x1, x2, not x3, x4, x5. The third clause here captures this third line, not x1, x2, x3, not x4, not x5. So I can write one clause for every combination of inputs for which the output is a 1, and then I can OR the lot. So the pluses over here represent ORs. Once I write it in this manner, then I can actually very simply compose an MLP for it. I have one perceptron for the first clause, one for the second, one for the third, one for the fourth, one for the fifth, one for the sixth, and then I can finally OR the lot, right? So what this means is that with just one hidden layer, I can compose any Boolean function, right? So any truth table can be expressed as a DNF formula, which means that a one hidden layer MLP is a universal Boolean function. But then how big will this network get? What is the largest number of perceptrons required in the single hidden layer for an n input variable function? For that, I'm going to represent the inputs in a different way. I'm going to represent them as Carnot maps. How many of you are familiar with Carnot maps? Anyone? Okay, some of you, right? How many of you have never heard the term? Quite a lot. So a Carnot map is a topological way of representing input patterns. This figure, for example, is a combination of 4 inputs: x1, x2, actually no, wx, y, and z, right? So these 4 rows represent every combination of w and x. These 4 columns represent every combination of y and z. And what you will observe is that if you look at any 2 adjacent rows, they differ in only 1 bit. In fact, the top row and the bottom row also differ in only 1 bit. So it's actually a cylinder. It circles. And similarly, any 2 columns also differ in only 1 bit. And in fact, the two columns at the edges are also connected. So the whole thing is a toroid. It's a cylinder in 2 ways, right? Now, this means that any pair of adjacent boxes and this figure differs in only 1 bit. So this is a way of representing a truth table of 4 inputs which have topological continuity. So there are four variables, 16 boxes, and the highlighted boxes are the combinations for which the output is 1. So in this particular case, there are 7 combinations under which the output is 1. So if I were to write this as a simple DNF formula, I'm going to have 1 clause for every one of the highlighted boxes. So if I had a single multi-layer perceptron with a single layer of single hidden layer, you would expect to see 7 neurons in the hidden layer. But then that's kind of naive because I can begin grouping things up. When I group things up, then the number of clauses in my DNF formula becomes smaller. These 4 highlighted boxes mean that because I can group these neighboring things up, what they're telling me is that regardless of the value of w and x, so long as y and z are 0, 0, the output is going to be 1, right? So I can group these 4 guys together and come up with a single clause, not y, not z. Similarly, if I group these 2 guys together, it's telling me that regardless of the value of z, so long as w is 0 and x is 1 and y is 0, the output is going to be 1. So this group tells me that not w, x, not y is a clause. And so by grouping all of these adjacent boxes together, I can reduce the number of clauses. I can reduce it greatly. And so now I have a DNF formula with only 3 clauses. A 1-layer MLP is going to have only 1 hidden layer MLP is only going to have 3 neurons in the hidden layer, right? What arrangement of bits can never be reduced in this manner? Anyone? How can I arrange bits in this so that the arrangement can never be reduced? By grouping. Okay. Diagonal? Actually, yeah, that will be part of it. Worst case. A checkerboard, right? No two neighbors can be connected. So I can never reduce the size, right? If I want to construct an MLP with a single hidden layer over here, for this Boolean function, how many neurons would I have in the hidden layer? 8, right? So if I have a DNF formula, one hidden layer MLP, I'm going to have 8 neurons on the hidden layer, right? This is a 3-dimensional version of a Carnot map. It has 64 boxes. And again, I've done the same alternating box grid pattern, chessboard pattern, right? So how many clauses do I have for which the output is 1 here? 32, right? And so if I want to have one hidden layer network, it's going to have 32 neurons in the hidden layer. In general, if I have n inputs and I want to represent a grid pattern of this kind, where any two adjacent, if one bit is flipped, the output flips, then my one hidden layer network is going to require 2 raised to n minus 1 neurons in the one hidden layer, which means the network is going to be exponential in the size of the input, right? But then let's take a look at this closely, right? If I want to use multiple layers, how many neurons will I need? These are XORs. The first figure is simply W XOR Y XOR X XOR Y XOR Z. The second one is the XOR of all 6 variables. And which is why flipping any one bit is going to change the output, right? And we know that an XOR can be composed using only 3 neurons, right? So which means that this network, W XOR X XOR Y XOR Z, can be done with 3 XORs. 3 for this first XOR. The output of that can be XORed with Y, which requires 3 neurons. Then the output of that can be XORed with Z, which requires 3 neurons. So in this case, I'm going to need 9 perceptrons, which didn't change things a whole lot. But then when I go to this bigger figure, here I have 5 XORs, right? Each XOR is going to take 3 neurons. So this, instead of requiring 32 hidden neurons and a total of 33 neurons, this can be done with only 15 neurons. But then, you don't quite get the import of this till you generalize. An XOR of n variables done in this manner is going to only require 3 times n minus 1 neurons, right? And so if you compare this, if I do this with a single hidden layer, I'm going to require 2 raised to n minus 1 plus 1 perceptrons. Whereas if I let the depth be greater than 2, then that's only going to require 3 times n minus 1 neurons. So something that required an exponential number of neurons, if you wanted to do this with one hidden layer, requires a linear number of neurons if you allow the depth of the network to vary with the input, right? If you allow the network to be deep. But then, how many layers will we need? Can we actually get an idea of how many layers is optimal? And what is the number of layers below which the net size of the network is going to blow up? For that, let me take the XOR problem again and let me rearrange the whole thing slightly differently. I can write my XOR in this manner. The XOR is associative, right? So the XOR of all of these variables, I can pair them up. So first I compute the XOR of the first 2 variables. Then I compute the XOR of the next 2, and then the next 2, and the next 2. Each of these is going to require 3 neurons. Then I XOR these outputs in pairs. Each of those is going to require 3 neurons with 2 layers. And then I can XOR those outputs in pairs and so on. So what is happening over here is that I'm grouping them in pairs. And each time I group them in pairs, I need 2 layers because the XOR requires 2 layers, right? So the number of layers I require over here is simply going to be 2 log 2 of n. This is the smallest depth I need for the network size to increase linearly with the input rather than exponentially. Now observe that if I'm using this very compact network formulation, if I told you that your network is only allowed to be 6 layers, regardless of the size of the input, then what happens? So that's like saying, or if I told you the network is only allowed to have 3 hidden layers, right? That's like saying that I'm going to XOR things in pairs, but after this, I allow you only 1 hidden layer. And what happened? And now what we observed was that when we use this associative formalism to group things together. At each layer, you're computing an XOR, right? So if I fix the number of layers at any point, from that point on, it's like having one hidden layer rather than arbitrary depth. And from that point on, you're going to require an exponential number of neurons. So anytime you go below this log n layers and you limit the number of layers to be below log n, the size of the network is going to increase exponentially in terms of the width if you want to compute the function. And the reason I've chosen the XOR is this. The XOR is a horrible function. If you get one bit wrong, the error is going to be 50%, which is to say totally random, right? Which means that if you miss one layer, if the permitted depth of the network is one layer less than the minimum, the network is going to behave randomly, perfectly randomly. So what we are finding here is that deep Boolean MLPs that scale linearly with the number of inputs can become exponentially large if you try to do the same thing with a smaller number of layers. And the problem is this, that pretty much any function eventually is going to have a structure of this kind, or almost every function is going to have a structure of this kind where you compute some Boolean subcomponents and finally you have an XOR. And from that point on, you're going to need depth. And if you terminate the depth at any shallow depth, the size of the network will have to be exponential for you to capture the function fully. So we begin to see what depth means in the case of Boolean functions, right? Now, I sort of showed this with pictures. There's math to it, of course. The XOR is really a parity problem. And any Boolean circuit of depth D using AND, OR, and NOT gates with unbounded fan n must have size at least 2 raised to n raised to 1 over D. That's the theory. And there's a lot of theory on it which says that parity is not an AC0, which means that you cannot compute parity, the XOR function, with a network that is fixed depth unless the network becomes exponentially large. So now, you can skip the slide. So here's a summary. An MLP is a universal Boolean function. It can represent any function, but for this, it must be sufficiently wide. For example, in the case of the XOR, if you want to have only one hidden layer, you need to have 2 raised to n minus 1 hidden neurons, right? Or it must be sufficiently deep. If you don't want to have that wide a network at each point, you will need to make the network deep. And if you try to go below a minimum depth or below the minimum width, the whole thing is not going to work. So the optimal width and depth depend on the number of variables and the complexity of the Boolean function. And so the story so far, MLPs are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine, but a single layer network may require an exponentially large number of perceptrons. Deeper networks may require far fewer neurons than shallower networks to express the same function. Now we saw this for Boolean functions, right? And they can we saw that deeper networks can be exponentially smaller than shallow networks. What about classifiers? Now, in the case of a classifier, again, the situation we saw is that a classifier is a function that finds a complex decision boundary over real inputs. And we saw that you should, in principle, be able to compose any boundary using a MLP, right? So we saw that if you just want a linear decision boundary, just a single perceptron should do it. The weighted sum of inputs must match a threshold, must exceed a threshold. If it exceeds the threshold, the output is 1, or otherwise the output is 0. So this is what a single perceptron captures, the boundary that is shown on the top right. And now, using that single perceptron, I can model more complex decision boundaries, like this pentagon, right? I can just have one perceptron for every boundary. I can OR them up. I get the pentagon. And then once I can compose the pentagon, I can compose more complex structures like this double pentagon, where I have one subcomponent for each pentagon and then I OR it, or even more crazy functions like this one, where, this is how I do it. I just decompose crazy decision boundaries into little polytopes and compose one subnet for each polytope and OR the lot. But then, can I do this with just one hidden layer? Now observe that the network I've just shown you has two hidden layers. And for other figures in higher dimensions, you might have more hidden layers, right? Can you do this with just one hidden layer? Let's take this simple example. Can I compose a network of the kind that I have to the right to capture this decision boundary? I'll give you a few minutes and let somebody guess how this would be done. Anyone? Is it possible? And if it's possible, how would you do it? Any guesses? Okay, I'm expecting no answers. Or should I? Okay, go ahead. It shouldn't. Yes. The x1 and x2 continues, as you can see in the figure. All right, let me give you the answer, right? Can you raise your hand if you're given up? Thank you. Let's see. So here's what I would do. Let's go back and look at the simpler problems. A diamond. If I want a diamond decision boundary, here's what I did. I had 4 perceptrons, 1 for each boundary, and then I ORed the lot. And so now observe that each of these perceptrons is going to output a 1 in a specific region. And only within the diamond do all 4 output a 1. Elsewhere, some of them output 1s and some of them output 0s. So here, in the diamond, the sum is 4. In these yellow regions, the sum is 3. And in these regions, the sum is 2. So if I actually plotted the sum is going to look like the figure to the right. Now, if I use a threshold of 4 and slice this off, I get the diamond decision boundary, right? If I do a pentagon, now observe again that the region where the sum is 3 is actually infinite in spread, right? Which is why if I use a threshold of 3, you're going to get some crazy kind of decision boundary. Now, if I were building a pentagon, I'd have 5 neurons. And so the sum of the outputs of the 5 neurons is going to be 5 inside the pentagon. It's going to be 4 in the yellow regions, 3 or 2 in other regions. So this is the sum over here, which I've plotted, right? If I use a threshold of 5, I get a pentagon. Yeah. You'd still get more than one hidden layer. You'd still get more than one hidden layer, right? So here's the key, right? We want only one hidden layer, so just hang on. If I do a hexagon, this is what it's going to look like. I have six perceptrons, 1 for boundary. The sum is 6 inside the hexagon, 5 in some regions, 4 in other regions, 3. This is the sum, right? That's a heptagon. I'm only plotting the sum. I'm no longer plotting the decision boundary that you get when you slice it, because obviously when I slice it at 7, I'm going to get a heptagon, right? What do you observe? The real problem is that with all of these figures is not the region where the sum is 4. The problem is the region where the sum is less than 4, but more than 2. Because if I have 2 such diamonds, then the 2 3s are going to sum up and become 6, which is greater than 4 and give you spurious regions, right? You want these strips to go down to the same as the floor. What happened? Yeah, you want these strips to go down to the same as the floor. When I go up to a pentagon, the size of those strips has gone down, right? As I go up to a heptagon, hexagon, or a heptagon, the size of these regions where the sum is not n over 2 keeps going down. That's with 16 sides. That's with 64 sides. That's with 1000 sides, right? And in the limit, it's going to, if I keep increasing the number of sides, then it reduces the area outside this polygon to the top and makes it smaller and smaller. And in the limit, you can actually stick a nice little mathematical formula to it. This is what the sum of these y's is going to look like. It's this crazy function over here. And it's going to look like so. When n is very large, it's like a cylinder which goes up and becomes a perfect circle in the middle, right? And it's a beautiful function. Now you can vary the width of the circle in the middle, and you can vary the steepness with which the function rises to the circle in the middle. And in the limit, you can actually make it something like a perfect cylinder. And so now, when n is very large, I have an infinite number of sides. I'm going to get the sum of the outputs of these infinite neurons is going to be a perfect cylinder. It's going to be n inside the circle and n over 2 outside. I can add an extra term which subtracts the n over 2. And now this is going to be an n over 2 inside the cylinder and 0 outside. Perfect, right? So now I can use two such subnets. One subnet which composes a perfect cylinder, say in this location. A second subnet which say composes a perfect cylinder in this location. I can sum up their two outputs, and that's going to give me a function which is two discrete cylinders. And this is all done with one hidden layer. Now, if I slice it and I say, output of 1 whenever the sum matches or exceeds n over 2, I'm going to get a decision boundary that's exactly 2 circles. And so now if I want to go up to this guy, this is how I'd have to compose it. There's no other way of doing it. And so this means I can compose any arbitrary decision boundary. It won't be perfect, it's an approximation. But I can make the cylinders smaller, I can pack them more compactly, and I can make the approximation arbitrarily precise. But with only one hidden layer. But the problem is that one hidden layer is going to have infinite neurons, right? Not of an exponential, it's infinite. So which means that MLPs can capture any classification boundary. One hidden layer MLP can model any classification boundary. So they are universal classifiers. But as you can see, going from just one hidden layer to 2 went from an infinite number of neurons to just 13, right? And so you can see why depth matters. Depth is key. You get the depth wrong, your network is not going to model the function, right? Now, what's the optimal depth and what can we say about activations? So what's the time? Okay, I'll stop. It is not a good time to stop. Can you guys give me 5 minutes? Right. The sleepier you are, the better the coffee tastes. Okay. Anyway, so let's take a look at some different patterns, right? Worst case decision boundaries for threshold activation networks. So let's take a look at this. Let's say I want this decision boundary, 1 inside the yellow, 0 inside the gray, right? How many neurons would I require if I just wanted one hidden layer? We just discussed this. Infinite, right? So clearly not a very good idea. But then also I have helpfully put it on the slide. It tells me how awake you are. Now, if I want to do this with 2 hidden layers, I can do this with 56 neurons. How so? There are 16, this hash is composed of 16 lines. So I can have 1 neuron for each one of these 16 lines. And then the boxes on top, there are 40 of these yellow boxes on top. And so I can compose this entire decision boundary with 16 first layer neurons to capture the 16 boundaries. and then 40 second hidden layer neurons to capture each of the boxes and or the lot. Now, so the total is 57 neurons, right? But this is just an XOR of all the various Ys which capture the individual boundaries. And so if I did this using a standard XOR network, that's only going to take 61 neurons. It doesn't seem like a win, but then when I go to something more complex like this guy has 64 with one hidden layer. This is going to take infinite neurons, obviously. If I use two hidden layers, it has 64 basic lines, which are combined into 544 yellow boxes. So the whole thing would take 608 neurons. Whereas if I did this with an XOR, I can do this with 253 neurons. And so, and basically, this is telling me that, I'm not comparing one hidden layer versus many layers now. I'm comparing two hidden layers versus many layers. This is just to give you an idea that even two doesn't give you the answer, right? Whereas the other figures might have fooled you into believing two layers are enough for any two-dimensional input. Not the case. So depth always helps. Regardless of the complexity, regardless of where you think you've achieved peak complexity, I can come up with an example where that is not enough. And so every case, a single network can require an exponentially large number of neurons. Deeper networks may require exponentially fewer neurons than shallower networks to express the same function. So deeper networks are more expressive. And then if you let me continue, since I'm going to I'm taking up more of your time than in any case, I'll take another 5. For continuous valued outputs, we saw what we could do with just one layer, with a function of one input, right? We could model pretty much any function. If I asked you to generalize this using the same theory to even a function of 2 variables, you would fail because this will not work. The way to think about it for a function of multiple inputs is to think again in terms of cylinders. So I can compose a cylinder with an infinite hidden layer network. And then if I want to compose an arbitrary function, I'm going to have to fill the function with cylinders of different heights and sum them up. And so even for a continuous valued function, if I want to do this with a shallow network, I may end up requiring infinite neurons to get it just right, right? Whereas if I permit depth, it can become trivially small. And then one final bit, which has to do with activations. I think I'll let spare you, and we'll talk about this after. All right. So I'm going to pick up a quick recap. We saw that neural networks can, even a single layer MLP is a universal function of, but more generally deeper networks require fewer neurons for the same approximation error. I'm going to spend a little more time on this before moving on. Now, we're going to speak about sufficiency of architecture. What does it mean to have a sufficient architecture, and what are the ways around it? Now, we saw that a neural network can represent any function, but the caveat is that it should have the architecture for it. Not all architectures can represent any function. So can somebody give me an example for something that we just saw of insufficient architecture in the first half? Yeah, even with one hidden layer, if I have fewer than the desired number of neurons. So for example, if I were computing an XOR, and if I had one neuron less than 2 raised to n minus 1 neurons in the hidden layer, then the XOR function would be wrong 50% of the time. Now, this is a Boolean function. For a Boolean function to be wrong 50% of the time means it's random, right? It's perfectly rubbish. So, but then let's go to real problems. We saw this network here, model here, which we said could be obtained using 2 layers with 56 neurons in total, 16 neurons in the first layer, 40 in the second. Now, instead of having 16 neurons in the first layer and 40 in the second, if I had only 8 neurons in the first layer, do you think I could compensate for it by increasing the number of neurons in the second layer? Does anybody think I could? So you're saying no, right? Why not? Because you have already lost information, right? So let me give you this example. Let's say I'm using threshold activations. If I'm using threshold activations, if I have only 8 neurons in the first layer, then those 8 neurons are going to be able to capture maybe these 8 lines shown over here. And those 8 lines can only give you this information. They can tell you which region of the space the input is in. If I'm speaking of using threshold activations, right? So which means it can tell you that you're somewhere in this red strip, but it won't tell you where in the red strip. Now that's a problem, because if you want to have the hash function, you need to know where you are in the red strip, and that information is lost. Now, even if those 8 neurons captured these 8 lines, all it would tell you is where you are in any of these regions, which is going to be insufficient to make the finer distinction between the sub boxes. You're going to be wrong 50% of the time. So, fine. Instead of 8 neurons, suppose I had all 16 neurons and I still had 2 layers. I had all 16 neurons in the first layer. If I have fewer than 40 neurons in the second layer, I'm still not going to be able to do it. Why? Because there are 40 of these yellow regions and I'm going to miss some. Of course, if I have fewer than 40 neurons in the second layer, maybe the error rate is not going to be 50%. So the deeper in the network you miss the neurons, the lesser the influence on the overall error, but you're still going to be unable to capture the function perfectly, right? And the reason for this, let's consider a case where you have fewer than 16 neurons in the first layer. Those, say I have only 8 neurons, those 8 neurons could at best capture these 8 lines. And so you won't be able to say, you will be able to say once you get past this layer that the input lies in this region, but it won't tell you whether, which of these 4 sub-regions you're in. That information is lost. And that has to do with the fact that I assume threshold activations, right? And a threshold activation only tells you, are you to the left of the line or are you to the right of the line? It tells you on which side of the line you're on, of the boundary you're on. It doesn't give you information about how far you are from the boundary. Now, if I were to use a different activation, so this is where the business of using activation functions that are not thresholds comes in. If I were to use a sigmoidal activation of this kind, then a sigmoid activation not only tells you which side of the boundary you are on, but for some distance, it continues to tell you how far away you are from the boundary. Now, if you have sigmoid activations, now in this case, what this would mean is that you're not only able to say that you're on the right side of this boundary, downstream, you would have information about how far you are from the boundary. And that information could potentially be used by downstream neurons to make finer distinctions. And so this means that the more information the activation gives you about how far you are from the boundary, the better it is for downstream, more information that downstream neurons will have to be able to learn the function. And so an activation like this one, like a ReLU, now is better than a sigmoid. The problem with the sigmoid is that after just a little bit, it more or less saturates to all arithmetic precision. And beyond a point, it doesn't give you information about how far you are from the boundary. A ReLU, for example, continues to give you information all the way out to infinity, how far you are from the boundary. Now, a ReLU is still has an issue to the left of the boundary. It doesn't tell you how far you are. So you might have encountered things like leaky ReLUs or other such functions, which also give you information on the other side. The only distinction is you want the function behavior to be different on the 2 sides of the boundary. But so long as the function continues to give you information about how far you are, those functions will actually provide information for downstream neurons to operate on. Which means that if I decided to have only 4 neurons in the first layer for the problem that I just gave you, right? If the 4 neurons in the first layer have activation functions which are continuous and give you information about how far you are from the boundary, then you can still capture the entire function by making downstream the later layers wider. And this, of course, recurses, which means that you can trade depth for width if your activation functions are graded, which is why we don't use threshold activations, which also explains why we get all of these papers in the literature which tell you, here's this new activation function, it does a better job. Because most of these activation functions are basically giving you information about distance from the boundary in the right regions of the space. So the lessons there, to add, deeper MLPs can achieve the same precision with far fewer neurons. And there's still limits. What is not stated over here is that there are still limits on how wide or what is the minimum width or the minimum depth the network can have. But these limits can be violated by having more graded activations. So long as the activations can give you information about distance from the boundary, you can still you can still learn the function. Now, there's more to it than that. And this has to do with learning the network. Now, a neural network can approximate any function. So I could learn a neural network to approximate the function shown by this grid, for instance. But if I want the neural network to approximate this function, I need to know the function at every point. And clearly, nobody is giving me the function. Most times when you're given a function to learn, you're not given the entire function. If you had the entire function, why would you need a network? What you are given instead is a bunch of input-output relationships. There's some unknown function, some classifier, some regressive, some unknown function. And you say, for this input, this was the output. And you're given a bunch of inputs and outputs, basically those red lines shown on the figure. And from just these red lines, you must learn the entire function. Now, the problem is that those red lines are not sufficient, right? The way we do it is we hypothesize some function. That's your initial estimate for the network. And when you hypothesize the function it learns is going to be off. And then you're going to adjust the network parameters such that the error at these points that you're shown, given as training instance, is minimized. You'd be minimizing the length of these little blue sections. But does that mean you're learning the entire function? No. Nothing is stopping you from learning this kind. So, given that, now, how bad is this problem? Your data are underspecified, regardless of the problem that you're given. And this means that you really have very little control over how the network behaves outside of the points that you have actually specified to the network. So how bad is this data underspecification? Let's consider a very simple problem where your inputs are binary. They're all 0 or 1. And let's say the input is 100-dimensional. 100-dimensional binary inputs are tiny inputs. Your standard image is going to have 1,000 pixels. And those pixels are going to be graded 0 to 255. So I'm speaking of a really, really, really tiny input. Now, on a 100-dimensional binary input, how many different input combinations can I have? 2 raised to 100, right? And so I'm going to have 2 raised to 100 inputs living on the corners of a hypercube. Every corner is a 0 or a 1. Every dimension is a 0 or 1. That's 10 raised to 30 possible inputs. If I want to specify the function fully, I have to specify the output of the function at every one of these 10 raised to 30 inputs, right? In the worst case, unless I can make some assumptions about the nature of the function. Now, suppose I give you, what is it? 1,000 trillion training instances, 10 raised to 15 training instances. Or is it right? That seems like an enormous amount of training data. 1,000 trillion training instances is like giving you no training data at all, because this is a trillion, right? Or a billion, billion, billion. So, which means that regardless of how much data you give me, it's incredibly underspecified. To give you an idea, I like to use this analogy. Let's say that all the data resided on a hypercube, where each side of the cube was some finite dimensional length. And then you were stuck in a little spaceship on this hypercube, and you're only allowed to travel along the edges on a speed of your choice, so long as it doesn't match the speed of light. And then I let you put you on a random corner and I say, okay, go ahead and travel along the edges of this cube and report to me when you find your first training data instance from the data instance that I gave you. The universe would end before you found your first training data instance. That's how sparse your training data are. You're basically given no data. And from that, you're being asked to learn the function. So if I were to scale this down, logarithmically, to say how much data I'm being given per dimension, it's like being given 1.000000001 instances per dimension. It's like being given one data point of this kind for each dimension, and you're told, learn the function. And you can see the absurdity of it. This doesn't make sense, right? This is what we're dealing with every single time you train a neural network or any machine learning algorithm. It's incredible that we actually managed to learn something useful. So given this, where do MLPs come in, and where does the structure of the MLP come in over here? We normally make some assumptions about the function. One of the assumptions we make implicitly is that if the output of the network over here is this much, then each data point represents a region of zero volume, right? Because a single point in any dimensional space has zero volume. We implicitly expand the volume. We say that if the output is exactly here at this point, if I take a small region around it, the output will not change much. So these are the kinds of assumptions we make, what we call regularizations, in order to be able to fill up the space so that you can learn a useful function. Otherwise, nothing would work. So neural networks actually end up imposing some kind of depth constraints, smoothness constraints through their depth. And that's because if I fix the number of parameters, let's say I say my neural network can only have 1 million parameters. I have a choice. I can make it wide and shallow, or I can make it deep and I can make it narrow and deep, right? Which one is better? It turns out that if you make the network deep, you actually get implicit regularization, because having a small number of parameters in any layer gives you a fairly crappy but smooth function. And then each subsequent layer kind of refines it. So what you would have if you have a deep network is that maybe the first hidden layer learns something really crappy, but it smoothed the space. Then each one is going to operate on the already smoothed output of the previous layer. And so as you go through the network, so long as you're learning the network correctly at the training data instances, at the other locations, the network learns to smooth the function and learn a much smoother function. Now, I can try to quantify this with equations and formulae, but let's do this visually. Here is a two-dimensional example. This is a decision region that I'm trying to learn. I want the output to be 1 inside the arrow and 0 outside. Now, this was done by Pulkit Agarwal and Jacob at Berkeley when they were in Berkeley. Examples, Pulkit's currently a professor in MIT. So you're going to have to trust guys who are currently professors in MIT to say that this picture is authentic, right? Anyway, so these guys actually put together various kinds of broad networks, and they drew 1,000 training points from this decision boundary. Training trick known to mankind to try to learn this decision boundary. And here's what they learned. It's beautiful, right? So here's another one. I know that I can learn this network using, this network can be modeled as a combination of a square and a triangle. And so we have an optimal structure, but this is what you learn for the parameters, right? This one is, I want a 1 inside the in the white regions. So this is basically a combination of 2 squares, one and not the other. So in principle, I can do this with about 12 neurons. But if I try to train that 12 neuron network using every trick known to mankind, I get this gorgeous decision boundary, which is not very useful at all, right? So, okay, having the optimal structure and having the right training algorithm still doesn't mean that you're going to learn anything useful, right? So what gives? What gives is that A, your training process is noisy. Secondly, We're just going to learn to be right at the correct at training instances, and everywhere else is going to be nonsense. The output is going to be nonsense. So now let's go back and look at how I can reorganize the same parameters to be something more structured. So these are different examples, but still you get the idea. Here I'm trying to learn this boundary. In this case, I'm trying to learn a boundary that looks like a bear. In all of these examples, there are 660 neurons. This is the decision boundary when I learn when I arrange my 660 neurons as 3 layers of 220 neurons. This is what I learn when I arrange it as 4 layers of 115 neurons. This is 6 layers of 110 neurons. This is 11 layers of 60 neurons. Which one works best? Clearly, the 11 layers with 60 neurons. Best job, right? Same thing over here. 660 neurons, 3 times 220, 4 times 115, 11 times 60, wait, and 6 times 110 and 11 times 60. And you can see that if I take the same number of neurons and I rearrange them to be narrow and deep, I get a much better approximation to the function than if I make it shallow and wide. These are all with the same activation functions. So again, there is a second restriction here. I need an activation function that carries information about distance from the boundary. So here we are using leaky ReLUs, using the hypothesis that we spoke of earlier. And again, what we are seeing is that for the same number of parameters, if you arrange it in terms of depth rather than width, then this incremental smoothing characteristic that the network has allows you to learn better functions, smoother functions. There's another way of doing it. Instead of using 1,000 training instances, if I use 10,000 training instances, it turns out that regardless of the network, you actually end up learning things properly. So the trade-off is lots and lots of training data, which you will never ever have, or arranging your network to have sufficient capacity, but the same capacity is better off arranged in depth versus then width. So now is official. This is the official break, right? This is what I was supposed to finish before the break. No coffee. Okay. Now, questions? Yeah. Yes and no. Yes and no. So here I've used some networks with the optimal number of parameters. For example, if I show you this guy, yeah. In this example, this had the optimal number of parameters. And I know by hand drawing the network that I can learn the perfect function here. But it didn't work, right? So it's not the number of parameters by itself, first. There's a second aspect to it. There are two different aspects to it which I've sort of conflated. One is the ability to learn the network. And the second is the ability of the network to actually represent the function. And so deeper networks are better able to represent these functions properly, but it comes at a cost. It's much harder to learn the network, which is why modern architectures use things like ResNet structures to let gradients flow so that you can actually learn the network. So provided you're able to learn, the deeper network will inevitably learn a better function. Again, with caveats, we'll see that in a few minutes. Questions? All right. So what does the network learn? Now, here's the problem again. You're given a collection of input-output pairs. You must learn the function, right? If I'm trying to perform classification, let's say I want to learn this double pentagon decision boundary, the one that we've seen earlier. What I really want to learn is a function like the figure to the right. It's badly drawn, but you get the idea. You want the output to be 1 inside the 2 pen, 0 outside. But you won't be given the function. What you will be given are the training data instances, those red and blue dots that I've shown in the picture, except the training data you get are never going to be this dense. Still, let's assume that they are, right? So you want to learn the classification boundaries that separate the red data from the blue data, except that you're not going to, the data you get are never going to be so clean. You're going to have some blue dots on the red regions and the red dots in the blue regions. That's the nature of life. So how do you learn the boundary, right? So let's just see what happens in this case. Let's unwind backwards to the simplest problem where you have a single perceptron. A single perceptron captures a linear decision boundary. So it's going to learn a boundary of this kind. There's a function of this kind. There's some linear boundary. On one side, the output is 1. On the other is 0. So the function it learns is going to be a step function, right? Like the figure shown to the right. Now here I've shown this with 2-dimensional inputs. Except that you won't be given the function, you're only given these training data instances. So you're going to be given some red dots on the one side, some blue dots on the 0 side. And from those data instances, you have to learn the function. So this is all you have. And just from those dots, from those training instances, you must learn the entire function. And if I'm speaking of a single perceptron. So when I'm speaking of a single perceptron, the parameters of a perceptron are simple, just the weights and the bias. And so you want to learn these weights W and the bias B such that the weighted sum of the inputs exceeds the bias or exceeds the threshold B on one side of the line, only on the red side of the line, and does not only on the blue side. So you want to learn a boundary which clearly separates the red and the blue, right? Now, let's see how we can do this. Let me restate it. I'm going to, instead of separately having a threshold term, I can explicitly capture a threshold term by adding an extra component. That's always fixed to 1. And the weight of that component will become your bias. So this is just sort of restating the problem so that I can get rid of this extra bias term. So then I'm saying, using this notation, I want the output to be 1 if the weighted sum of inputs is positive and 0 outside. And I want to learn of this kind, which is going to separate the red from the blue, right? So basically, what is this? This equation over here represents a boundary. And the boundary is where summation Wi xi exactly equals 0. The boundary is where the weighted sum of inputs is exactly equal to 0. So you're saying learn a boundary of this kind such that all the red dots fall on one side, and all the blue dots fall on the other side. And you can state this again in algebraic terms. I can represent these weights W as a vector, these weights Wi as a vector W, the components of the input X as a vector X. And you want then the boundaries represented by this equation W X equals 0. The between W and X is 0. Now, when is the inner product between two vectors 0? Anyone? They're exactly orthogonal to one another, right? They're at 90 degrees to one another. So this means that I'm trying to find the vector W such that the hyperplane that's at 90 degrees to the vector cleanly separates the red from the blue, right? And specifically, how do I know which is red and which is blue? We're going to use this decision rule that if the inner product between the weights vector and X is positive, I'm going to call it the positive class. If it's the red class, if the inner product is negative, I'm going to call it the negative class, the blue class, right? So what this means is that if this is the weight vector, if the angle between this data instances and the weight vector is less than 90, I'm calling it class 1. If it's greater than 90, I'm calling it class 0. Easy enough. So now, using this rule, what is the optimal weight vector for any given training instance? If I have only a positive training instance, then the optimal weight vector will point exactly at that instance, right? Because that's when I guarantee that it's on the correct side of the plane. This is going to give me the maximum boundary. On the other hand, if I have a negative training instance, the optimal weight vector is going to point exactly away from that instance. This is what guarantees that the inner product is definitely greater than 90 degrees. It's actually going to be 180 degrees, right? So this is the simple rule. For a positive training instance, the optimal weight vector points at the instance. For a negative training instance, the optimal weight vector points exactly opposite to that instance. And visually, it must be obvious why this is the case. We are simply going to use this rule iteratively. So here's what I would do if I wanted to learn the boundary given a bunch of training instances. I'm given a bunch of training instances xy, x1, y1, x2, y2, and so on. I'm going to use the label +1 and -1 rather than 1 and 0 for the training instances, for the labels, right? I cycle through the training instances, and I'm going to check each training instance. Is this correctly classified? If the training instance is correctly classified, my current boundary is fine, right? This is sort of following Rosenblatt's rule, right? You only correct for the error. If the training instance is incorrectly classified, then I know that for a positive instance, I want the weight vector to point at the instance. So for a positive instance, the optimal weight vector is x itself, right? So I'm going to drag the current weight towards that instance by adding x to it. For a negative training instance, I know the optimal weight vector is exactly opposite to it. It must be -x. And so if a negative training instance is incorrectly classified, I'm going to drag this weight vector towards the optimal weight vector for the negative instance. So I'm going to say w equals w minus x. Simple rule. Nothing fancy, right? Is it making sense to everybody? And where the logic comes from? And so if that is the case, then here's what it would look like. I have, say, these training data instances. I'd initialize my weight vector somehow. And I sort of loop through my training data. And I use the same classification rule. I check the sign of the inner product between w and x. And I scan, and I find that this blue instance, here I've sort of flipped positive and negative, so blues are positive. So the blue instance, which should be a positive, is being misclassified as a negative. So if it's being misclassified as a negative, I know that the optimal weight vector for this instance is this guy, right? So I'm going to add this thing, the optimal weight vector for this misclassified instance, to the original weight vector. And that gives me the new weight vector and the new decision boundary. Then I cycle a loop through my training instances again, and then I find that this instance, which is a negative instance, is being misclassified. It's falling on the positive side of the boundary. The optimal weight vector for this instance is going to be the exact opposite, the negative of the arrow pointing to it, right? So I'm going to subtract that weight vector from the current weight vector. That gives me this new decision boundary, and now everything is perfectly classified. No more corrections to be made, right? It's a very simple algorithm. This is the famous Perceptron learning rule. And you see where the intuition comes from and how it works. Now this, if the red dots and the blue dots can be separated by a hyperplane, then this comes with a guarantee. It guarantees that this algorithm will converge and find a plane that separates the positive and the negative classes in a finite number of steps. And specifically after a number of steps that is proportional to the square of the distance of the longest input vector, meaning the one that's farthest away from the boundary, and inversely proportional to the margin. The margin is what you're familiar with from support vector machines, to the square of the margin. Anyway, so intuitively it takes several increments of step of several increments of step size equivalent to the margin to eventually correct for everything. But nonetheless, in a finite number of steps, you're guaranteed to find the correct answer. The real issue is that in real data, data are not going to be separable by a real line, by a hyperplane. So you'll find data of this kind. You'll find some red dots hanging over, in space, hanging in the air on the blue side. You'll find some blue dots sitting on the floor on the red side, which means that if you use the Perceptron rule, it's going to keep cycling because it keeps finding errors. The data are not separable. You're never actually going to find an answer. It will loop forever. So how do we deal with this situation? This is where our standard learning paradigms come into play. So let's go back and look at a very trivial one-dimensional example where I'm trying to separate these red dots, which belong to class 1, and blue dots, which belong to class 0. Now, in a one-dimensional example, what is a linear classifier in one-dimensional space along a line? Anybody? It's just a threshold, right? So you're trying to find a threshold that separates the red from the blue. Is there a threshold here? There is no threshold, right? So now we know that our neural network is an infinite capacity. It can be, it can model any function. So if I give it enough neurons, there's nothing stopping my neural network from learning this function. Is this what we want to learn? Clearly not, right? This is rubbish. So this is what we call overfitting, right? We are very familiar. It happens all the time. So how do we deal with this? To deal with this, let's ask ourselves an extreme question. Let's assume that I'm willing to tolerate this. If I'm willing, and this is a perfectly acceptable answer for me. If this is a perfectly acceptable answer, suppose I gave you this situation where I have 100 training instances, all of them have the same X. But of these, 90 of them are red and 10 are blue. What is your function going to be? Because now there's no unique answer, right? For some training data instances, it's going to be 1. For the other, it's going to be 0. Should I be choosing 1 as the answer? Should I be choosing 0 as the answer? Or should I be saying 0.9 to indicate the fact that 90% of the time it's red? What would you choose? Anyone? What would you choose? Because that carries the most information, correct? So that's basically what you would want to do. So you want to use 0.9 as the answer, right? But then, why does 0.9 make sense? 0.9 basically gives you the a posteriori probability of 1 given X. You didn't think about it explicitly, but that's what it was. Now, let me change things a little bit. I jitter all of these 100 training instances at this point by 10 raised to minus 17, which is the limit of floating point precision, right? I still permit my network to go up and down like mad. Does it make sense to give an answer greater than 0.9 simply because everything is off by the limit of arithmetic precision? Would you accept that? I'm assuming not. Silence is yes or silence is no, depending on what I want it to be. Right? So it doesn't make sense, right? So when I jitter it, I still want 0.9. Then once I agree that jittering it should permit the answer to still be 0.9, how much jitter do I accept before I say it has to change from 0.9? There's no answer to it. What we have to do is to change our perspective. So instead, I'm going to look at something else. I'm going to look at a small window. I'm not specifying the width of the window around each position X. And within that window, I'm going to ask myself, how many of my training instances have the value 1? And that is my guess for the a posteriori probability of y equals 1 given X. And as I slide this window left to right, I'm going to find that proportion changes in this manner, right? That's what the curve looks like. And so this is what I would like my perceptron to capture. What does this look like? This is your sigmoid, right? And so the sigmoid is this lovely function where, it's 1 over 1 plus e raised to minus x, or this affine function of x. When the argument of the exponent is a large negative number, e raised to minus of a large negative number is infinity, so this becomes 0. When the argument of the exponent is a large positive number, e raised to minus large positive number is 0, so it becomes a 1, right? So it gives you a nice sigma, and so it gives you the kind of behavior that you want to see over here. And in fact, if I have a perceptron where I use a sigmoid as my activation function, and you're all very familiar with the sigmoid, this actually captures the a posteriori probability of the class 1 given the input X. Now, of course, you're going to ask me, what was the width of this little window? We'll never consider it explicitly. We're just going to depend on statistics, right? And we'll see how in a minute. But then that was for one dimensions. The same idea generalizes to multiple dimensions. If I have a two-dimensional example with, say, two-dimensional inputs where I want a linear classifier separating the red from the blue, but I have some red dots on the blue side, some blue dots from the red side, then no hyperplane, no plane will clearly separate the two colors. A sigmoid logistic function, a sigmoid activation function, actually learns this sheet, sigmoidal shaped sheet as the function. That's what it represents. And although the function that it represents is not linear, it represents a linear decision boundary. Why so? If I say take the boundary as, where y equals, say, 0.5, then you'll find that the locus of points where y equals 0.5 is an exact line. So although the function itself is nonlinear, if I equate the function to any threshold to decide where the boundary between 1 and 0 lie, that's always going to be a hyperplane. So it's a linear classifier. Anyway, going back to the one-dimensional case, just for purpose of illustration, this is our function. We have the sigmoid function, which captures the posterior probability P of y given x. And it has this form, 1 over 1 plus e raised to minus of w0 plus w1x. So w1 tells you how much to scale the axis by, and w0 tells you where to position the center of the sigmoid. That's it, right? And now if I want to learn this function, I want to learn w0 and w1, which tells you how fast the sigmoid increases and where it must be centered. Now, this is P of y. This guy is P of y equals 1 given x, right? That's y equals 1, P of y equals 1 is 1 over here, 0, 0 out here. So what is the equivalent of P of y equals, and we're going to use the 1 and minus 1 labels. What is the equivalent of P of y equals minus 1 given x? It's going to be 1 minus P of y equals 1 given x, right? So P of y equals minus 1 given x is going to be 1 minus this term. If you work it out, that's simply going to be the same as this equation, except instead of a minus, you will now have a plus. It's very easy to show. So I can actually write both of these together. Is this making sense to everyone? Right. So I can write both of these together in a common form, which says P of y given x equals 1 over 1 plus e raised to minus of y times w0 plus w1x. And you can see when y is 1, it gives you this equation. When y is minus 1, it gives you this equation, right? So I've written both jointly. And now I have a bunch of training data. And the x's are vectors, y's are binary. Actually, think of these as 1 and minus 1, not 0 and 1. The total probability of the data is going to be, assuming that all of my training data are independent, it's going to be the product over all training instances of the product of each training instance, of the product of the probability of each training instance. That is P of y comma x. And P of y comma x can be written as P of x times P of y given x. And P of y given x is simply a sigmoid. So far, so good, right? This is the joint probability of all of my training data. And so if I take the log of the joint probability of all of my training data, that's going to be the summation over all training instances of the log of P of x minus, because this term is in the denominator, the summation over all training instances of the log of this denominator term computed at each x. And so this, using the standard maximum likelihood principle, what I'm really learning is a probability distribution for the data. And what does the maximum likelihood principle state? The maximum likelihood principle states that I must learn the parameters, the model parameters, such that they maximize the likelihood of my training data, right? So that means that I must learn my model parameters W0 and W1 to maximize the log likelihood of my training data. Now, of course, this first term is not a function of the model parameters. So I only need to worry about these guys, right? And so that's like saying I'm going to be maximizing the negative of the sum of these log terms, or alternately, minimizing the sum of these log terms. I won't get into what the term, I won't read the term out, but you'll have to believe me if you're in this. This is basically just the cross entropy between the labels that are provided and the labels that are computed by the network. And so this is identical. This minimization is identical to minimizing the cross entropy between the desired output y at each training data and the actual output of the network. So what does this mean? It cannot be solved directly. It needs gradient descent. What this means is that when I'm trying to, if I learned a perceptron with a sigmoid activation and just use standard gradient descent as you would if you just threw PyTorch at it, what you're actually performing is maximum likelihood training of a statistical model. You're performing maximum likelihood training of a model that computes the posterior probability of y given x. But in fact, you're performing maximum likelihood training of a model that computes the joint probability of x and y. So you may not have thought about it when you implement it, but this is in fact what you're doing. So it's all very fine for a single perceptron, right? But suppose I have something more complicated, like this guy here. This is trying to learn the double pentagon decision boundary, except I have data leakage. I have blue points on the red side, I have red points on the blue side. So what happens here? Now, before I go into this leaky situation, let's consider the clear case, where the red and blue are clearly separable, except that you're only given the data points and you must learn the boundary, right? So, and you're trying to learn to classify. Now consider the case of a sufficient net. We know that this decision boundary can be captured by this network architecture shown to the right, where one subnetwork captures one pentagon, the other subnetwork captures the other pentagon, and the two are ORed by the final perceptron on the top, right? But we know that this perceptron, regardless of whether it's using a threshold activation or a sigmoid activation, is a linear classifier. We just saw that perceptrons are linear classifiers. That's what we've been talking about for a very long time. So if that is the case, then what can we say about the features that are being input to this final perceptron? Anyone? That final perceptron is able to separate the red from the blue, right? So what can we say about those, the output of those two penultimate perceptrons? Anybody want to take a guess? Must they be linearly separable? They must be, right? So what this means is, if you look at the y1, y2 space, the reds and the blues are going to be linearly separable. Otherwise, your network would not be doing the job it was supposed to be doing. This got hidden when we were looking at it from a Boolean perspective. And so what this means is that the rest of the network is performing which are tangled and moving them around so that by the time you get to the classification layer, the data are linearly separable. And so the rest of this network can be viewed as a transformation that transforms data from non-linear classes to linearly separable classes. What used to look like this figure to the left ended up looking like this figure to the left. It moved the blue and the red so that you could draw a boundary that separated the two. And once you've trained this network, once you've learned this network, it means that you could actually use any kind of linear classifier. It didn't have to be a logistic function. It didn't have to be a perceptron. You could have thrown in an SVM. You could have thrown in any linear classifier. Because no, but that by this point, the two classes are linearly separable, right? And now this is true of any structure. So in this case, I showed you the optimal structure. But if I gave you any other sufficient structure which had more than the required number of parameters, and I trained this network to separate the red and the blue classes, and it did a perfect job, the assurance is that that portion of the network below the final classification neuron is actually doing the job of moving the data around so that they are linearly separable. That is the only condition under which the final neuron could actually separate the classes, right? So what if I have insufficient structure? So here, for example, let's say instead of having 10 neurons, I had only 9. I know that with 9 neurons, I cannot separate the classes. Nonetheless, when I try to learn the classes, it's going to try to move things around so that as far as possible, these guys are linearly separable. It will fail, but yeah, it's still going to be non-random. But anyway, so mathematically, here's what happens. This final neuron is basically learning a logistic function, and the data are going to be assumed to be linearly separable in the space of Y. And so the network until the second to last layer is a non-linear function that moves the data around so that they are maximally linearly separable. In some cases, if the network architecture is insufficient, they will not be exactly linearly separable, but nonetheless, it's going to be close. And very often, you do not want the network to have sufficient structure to make the classes perfectly linearly separable. Why is that? So if I go over here, I can assure you that even for this nasty example here, way back when, I can always have a network which moves the reds and the blues around so that by the time they get to the final layer, they are linearly separable. So having a sufficient architecture is not always a great thing. A sufficient architecture can actually end up giving you overfitting. What we often need in situations like these is an insufficient architecture, which is incapable of separating the classes, because that's what is going to give you a more generalizable function. So there's a lot of non-intuitive stuff that happens in these learning problems. Now, there's something else interesting over here. So this is the more typical setting for classification problems. I'm showing this as 2 fuzzy pentagons. You must think of this in general as a classification problem where the network is insufficient to do a perfect job on your training data, because as we saw, a sufficient network can actually end up giving you overfitting, right? So in that case, what's happening here? The final neuron, the Y out, is still computing posterior probabilities of the class given the output of the boxed region of the network, right? And so you can think of the boxed region of the network as a feature extraction block that transforms the data such that the posterior probability of the classes may now be modeled by a logistic function. And so overall, the feature extraction layer or block transforms the data such that the data end up looking something like this at the output. And then the rest can actually be modeled using a posterior probability. So what does this mean? The output of the network is still going to be P of Y given X. In fact, this is a logistic function, so it's going to give you a probability of the posterior probability of the class given these guys. But these outputs are deterministic functions of X, right? So overall, this network still gives you the posterior probability of the class given X. So when you train the network, although we are using gradient descent and backpropagation and all the rest of it, the network is still learning its parameters to optimize, to maximize P of Y given X. So what this means is that, again, while you might not be thinking explicitly of it, training the network is actually a statistical exercise. What you're always doing is to find the parameters that maximize the conditional probability of the label given the input. So in other words, and classification MLP actually comprises 2 components: a feature extraction network that converts the inputs to almost linearly separable features, and a final linear classifier that computes the posterior probability of classes given the input. And the neural network is actually a probabilistic model. It's learning the conditional probability of Y given X, assuming that it's not explicitly modeling the probability of X itself, only P of Y given X. And every single training paradigm that you use is eventually trying to learn the network parameters to do the best job of computing P of y given x, the posterior probability of y given x. So far, so good. So we know what's happening until here, right? The features must be almost linearly separable at that point. What about below that? What happens below this? They too compute features, but how do they look? So now here's the interesting thing. We know that these data at x need not be linearly separable. We know that by the time they get to this region, to the y's, what I have as y's in my figure, the classes must be perfectly linearly separable or almost perfectly linearly separable. So what happens in the middle? The hypothesis, the manifold hypothesis, says that when I have data in some space, there's some curved surface in the space on which the classes are linearly separable. And so what the network is doing is sort of slowly straightening this up so that by the time you get to the output region, you actually have straightened out the manifold, and on it, all the classes are linearly separable. So let's see what actually happens. I'm going to give you a little toy example. In this case, we're trying to learn the circular decision boundary on top. You want the output to be 1 inside the circle and 0 outside. I have a 1 hidden layer network, which has 3 neurons in the hidden layer, and the 3 neurons have a tan H activation. And then I have a final final neuron which combines their outputs. Now, what happens when you use this network? There are 4 steps. In the first step, your input is in 2 dimensions. Because I have 3 hidden layers, the first step computes a 3-dimensional representation through a linear transform of my 2-dimensional input. That's the affine transform, right? In the second step, I have an activation that's applied this 3-dimensional input to this 3-dimensional representation. Then in the third step, after applying the activation, I still have a 3-dimensional representation, right? Then in the third step, that 3-dimensional representation is now projected down to 1 dimension through a linear transform. And then finally, I applied a threshold activation on it, or a sigmoid. So if I start this 2-dimensional input here, if I start off with this 2-dimensional input here, and I apply my first linear transform, when I move it up to 3 dimensions, even in 3 dimensions, it's still going to look like a 2-dimensional plane in 3 dimensions. Because if I take 2D data and multiply it by a 3x2 matrix, I'm not increasing the amount of information. Now I'm going to get a 2D plane in 3D space, right? And then I apply a tan H activation to every single point on the space. That's going to warp the space, warp the surface. So this is going to be the warped surface. And then this warped surface is going to be projected down by a 1x3 matrix to a single line, to a single dimension. And then I finally apply a threshold to it. So if I applied a threshold on this guy, then everything to the right is going to be marked as red. Everything to the left is going to be marked as 0, right? So when I initialize my model, here's what I have. This 2-dimensional plane has been projected into this 3-dimensional surface. This 2-dimensional surface in 3D space. When I transform each of the points using a tan H activation, the new coordinates look like this. It's no longer a plane, it's a curved surface. Then when I project this curved surface to a line, it looks like this guy here. When I apply a threshold, the decision boundary I get is this, right? So everything to the right of some point is red, everything to the left is blue. And then if I work my way back, it looks totally crappy. But then let's see what happens during training. The top left box just shows you the loss. And see how it's searching through the space of all transformations from 2D to 3D. So that it's trying to figure out how to position the plane in 3D space. So that when you position the plane in 3D space and then warp it using the tan H function, and then project the surface down to 1 dimension, the blues and the reds separate out. And now a threshold cleanly separates the blues and the reds, and you get the right decision boundary, right? So basically, it took a surface And then it sort of searched around such that when you stretch it out using the tan H activation and then project it onto a line, the blues and the reds come on different sides of a single threshold. So that's basically what the learning is doing over here. You can see this. You can see that as it searches, the separation between the blues and the reds on the projection, actually comes out very cleanly. So as it goes through the space at each point, this is with just one hidden layer. After the first hidden layer, there is linear separability between the classes. The second class, the output layer simply separates the classes. If I increase the number of classes, here's what happens. This is for Sapphire. This is 11-layer network, and each color represents a dot. And let's see what happens to the dots as I train the network. That was too fast. The animation's too fast, but you can see that as you go through the network, the classes separate out and begin to get linearly separable. So this is projection in 2 dimensions. Let me actually show this in 3. This might be better. And you can see how the classes sort of separate out as you go through the layers. And each layer increases the layer separability between classes until eventually all the classes are linearly separable. Now, the interesting thing over here is that during training, the linear separation between classes is increasing. And what is not apparent from this, thanks to the speed of the animation over here, is that the classes became linearly separable at the final layer fairly early. But when I continued training beyond that point, they actually began getting to be linearly separable in earlier layers as well. And so I don't know if you can see this. If you blink really, really fast, once per frame, you might capture this, right? And so it got linearly separable over here, and then here, and then at this point, it's actually linearly separable. So here's the fun thing. I could train the entire network and then throw away the last 3 layers and then reattach a linear classifier. And I'd get a much smaller network, which would have the same accuracy, because it's, the overtraining has actually managed to push the linear separability back through the network, which is an interesting phenomenon, which is not very often reported, but happens every single time. So, questions? Yeah. So it actually ends up being less effective. So the whole point is that when you over-parameterize it then it learns better. This is one of those things that we've learned with experience. In principle, it should happen. In practice, this is what we get.
Thank you.
Is this an indication of overfitting though? When you get like additional layers?
It's not really, because what happens is that if you think about the activations, it moves all the data eventually to the linear portion of the activation. All of these are ReLU activations. So you have the data all over the space, and then it slowly moves them into the region where the activation is linear, where the layer basically becomes redundant. This is a common phenomenon, not just in neural networks, but in all machine learning models. So if you poked around with boosting, adder boost, for example, you would have been taught that when you continue to train the model way beyond the point where the training error is 0, the generalizability of the model increases. That's because although it has managed to do a perfect job of separating the classes, the additional components are increasing the margin. So that's something to observe over here as well. Any other questions? I have not tried, so I can give you an answer, but it would be BS. Yeah, there's another question. All right. That's an interesting question. I should think about it. You're the first person to have asked. How do you relate it to double descent? So double descent is this phenomenon where the network actually seems to, the loss seems to saturate, but then as you keep training it, eventually it takes another plunge. And the difference really over there is the difference between learning a generalizable function and then learning to really, really memorize. And memorization is a completely different thing. Now, it turns out, actually, just from the examples that I've given you today, it should be very easy for you to tell me why it's possible to memorize a training data set with n training instances using order n neurons in one hidden layer. And that's because for every single training instance, I can just surround it with a polytope. And I can put every single training instance within a polytope of finite size, with a linear. And the size of the polytope would just depend on the dimensionality of the space. And so the size of the polytope and the number of neurons needed for each polytope is constant. And the number of polytopes is going to be proportional to the number of training instances. And then I can OR them up. So using just one hidden layer and order n neurons, I can memorize any training data at all. Whether that's useful or not is a different thing, right? And so the double descent sort of relates to it. Any other questions? Yeah. This one? So this is, okay, I don't have a board, otherwise I could write this. But think about what you actually do, right? When you're implementing this, you have X. The first operation you're performing is WX, that's your linear layer. WX is a linear transform, right? It's an affine transform. So that's going from the 2D to 3D. And searching for W is basically positioning the plane. And then you're doing a tan H of that. So there are ways of actually learning the activation function, but then that just increases the complexity. It's a different beast at that point, right? So for a given activation function, this is what is happening. If you're learning the tan H, then there are many ways of doing it. I could be picking from a pool of activations. I could be learning the shape of the activation. Each of these just increases the number of parameters. So there's no clear comparison here. Yeah. But yes, there are intuitions to be developed along those as well, but it doesn't add a lot to this. Yeah. All right, let me continue. So we've seen what the network learns out there at the output, classification or regression. It can do anything. We've seen what it does, that we've seen that the box below the output transforms data to be separable. And we've learned that as the data goes through the network, at each point, the classes become more linearly separable. But what do the individual, that's at a statistical level, right? What do the individual neurons learn? For that, let's go back and see something that we saw early in this lecture. If I use the threshold activation, I like to use the threshold activation because it's a very intuitive way of explaining things. So if I use the threshold activation, each perceptron fires if the inner product between the weights and the input exceeds a threshold, right? And that's the same as saying that each perceptron fires if the cosine between the input and the weight is less than a threshold, which in turn is the equivalent of saying that each perceptron fires if the input looks like its weights. The more it looks like the weights, the more it's likely to fire. In the best case, the input is going to look exactly like the weight. That makes sense, right? So which is why when I'm trying to build a classifier for the digit 2, I don't have to learn the classifier. I can just use a single perceptron and set the weights to be, and I'm guaranteed that this is the optimal thing I can do because it's going to be matching the input to the digit 2. Because that's what each perceptron is individually doing when you look through the math, right? So this gives us a lovely bit of insight. Let's say I have a network whose job in life is to look at these LCD patterns and to determine if the input is a valid digit or not. Now, in this case, what would you expect the network to learn? You'd expect the first layer neurons to learn some useful features, you'd expect each of the neurons in the first layer to learn to detect which clearly indicate whether the input is a digit or not. So you'd expect that maybe, you know, if I have these seven neurons, they'd recognize each of the seven vertical and horizontal bars that constitute a digit. Or if I had more, they may also learn to recognize these crazy diagonal patterns, which are never seen in digits. Because if you saw those, then it means it's not a digit, right? And the rest of the other things that are kind of noise and irrelevant will never be detected. But then here's the thing. Now, if I've got this network, I know that those 7 neurons are actually capturing patterns in the input, right? So let's look at this guy. Consider this guy. This neuron is looking for this horizontal bar on top of the LCD pattern. So if the neuron fires, what does it tell me? Has that pattern occurred or not? It has, right? So if I just went through each of the neurons and say I just drew another empty box of LCDs, and then I just inspected the output of each of these neurons. And if I found that this neuron fired, I put a vertical bar. If I found that this neuron fired, I put a horizontal bar, and so on. I basically recompose the input based on which of these neurons fired. Would I be able to recompose the input? What do you think? Only, yes, in this case, so this is what it would look like, right? The neuron fired, I'm going to be recomposing it with the weight pattern for the neuron. So this is what the network is going to look like, right? The output weights are the transpose of the input weights. And you would expect it to recompose the inputs only, but only if the inputs were exactly digits or clearly not digits. Features that were not relevant to this particular task would never actually be captured. But within that, you can. What's happening here? Within this these parameters, you would be able to recompose the input or much of the input depending on which neurons fired. So can I formalize this to actually make the network recompose the input? This is what we'd call an autoencoder. I'd make this explicit. I want to recombine the outputs of these neurons so that the output is exactly the same as the input. This is an autoencoder. And the autoencoder has 2 components, the encoder, which learns to detect all the most significant patterns in the input, and the decoder, which learns to compose them back to reconstruct the input. So now an autoencoder is a beautiful thing. Although autoencoders are not exactly classifiers, they give you a very good idea of what kinds of features the network actually learns. And in fact, before we got great gobs of data we have today, neural networks already began to become a big thing in the early 2010s or the late 2000s, because Jeff Hinton and co discovered that prior to training a network for classification, if you train them to perform autoencoding, then the initial point that you got was fantastic to train the network. Without that early step, the network wouldn't learn to do anything useful. But with that additional step, it actually learned very quickly to perform the tasks properly. And that's because in the process of performing autoencoding, it actually learned the features that were relevant to the data. And then those could be bootstrapped into performing classification. And so it's good to look at autoencoders because the kinds of features they capture tell you something about what's happening inside the network, right? So let's train a neural network to explicitly predict the input itself. You have an encoder which detects features and a decoder which recomposes them, right? Now, to understand how this works, let's consider the simplest autoencoder. I have just one neuron rather than an entire layer of neurons. So I have one single hidden input, which is also the output. And to simplify matters further, I'm going to assume a linear activation, meaning there's no nonlinearity. It's just a weighted sum of the x's, okay? So if I do this, then what is the output of the network? The output of the network is going to be, the output of the hidden layer is going to be Wx. the output of the network is going to be W transpose WX. If I try to minimize the error between the input and the output, it's going to be X minus W transpose WX squared norm. And minimizing this, anybody who has done any linear algebra, you will know that this is just principal component analysis, right? So a simple one single neuron autoencoder with linear activation is finding the first principal component. That does. And specifically, if you look at what is being reconstructed, anything that's going to be reconstructed is going to be some linear extension of the vector W, right? So which means that all reconstructions are going to just lie on some linear extension of W. So regardless of where the data lies, every single output is going to be on this line. Everyone with me? This makes sense? Questions? I'm going to assume you got this because I'll go from here. Okay. And so this is going to be a principal component, right? And in fact, this will happen even if the input and the output weights are very different. If you set the input and output weights to be different when you train the network, you're still going to be performing principal component analysis, and the output weights are going to be the principal direction. Okay. Now, suppose instead of having just one hidden neuron, I have multiple hidden neurons. What will it learn? Using the same math, it's still going to be performing principal component analysis, except it's going to be learning the principal subspace rather than the principal component. And the dimensionality of the principal subspace is going to be the same as the number of neurons in the hidden layer, right? So far so good. And here's the key thing. The output is going to be some function of W transpose, right? So the output is always going to be this principal subspace, which means regardless of what the input is, the output is always going to be on this pink sheet onto the principal subspace. Regardless of what input you give it, it can only reconstruct outputs on the principal subspace. So again, terminology, if I have many such neurons in the hidden layer, this portion, which obtains a representation of the input, is what I'll call the encoder. This portion, which reconstructs the input from it, is what I'm going to call the decoder, right? The synthesizer. Now, so far I've assumed a linear activation. What happens if I introduce a nonlinear activation? Nonlinearity, as we saw in the case of the tan edge, distorts the space, right? It distorts the surface. You remember this from the tan edge example? In the tan edge example, this was what we had. Going back many slides. Yeah. This planar region over here got distorted by the nonlinearity, and it made it warped, correct? And so regardless of, so that concept is still going to hold over here. I'm going to assume that the nonlinearity is part of the decoder. And so what the nonlinearity will do is to take this principal component subspace and fold it in some manner. And then you're going to learn to reconstruct inputs such that the error between some point on this folded space and the reconstructed input is minimized. So what does this mean? Now, this is also principal component analysis, but it's not linear. It's no longer finding a linear manifold that the data lie on. It's finding a nonlinear manifold. It's performing nonlinear PCA. So that's basically what a network is kind of doing. It's folding the space and finding the nonlinear principal components. And in fact, the deeper you make the network, the more nonlinear, the funkier thing it can do on your data, and the more nonlinear the subspace that it can, the manifold that it can actually learn from the data. So for example, here's an example where my data lie on the spiral. And as you can see, it's a little bit of noise on the spiral. Now, how many degrees of freedom do I have? I actually have only 1 degree of freedom, which is the distance along the spiral, right? So I'm projecting this down to one dimension using an encoder. This is a 64 2 cross 64 encoder and a 2 cross 64 decoder in this example. And so at this point, there's just one component. And then this is the decoder which reconstructs the input. And you can see that the decoder reconstructed input is exactly the spiral. It's always on the spiral. But there's some strange things going on. It has to do with training. There's no guarantee that your network is going to learn the kind of logic you have in your mind. If I just took this trained decoder and varied this input from minus infinity to plus infinity, do you think it's going to keep forming a spiral? Not at all. So when you go outside the range that you saw in the training data, it begins to do strange things. And even within the training data, in little gaps where you don't see data, it can behave strangely. So here, for example, it went up this spiral, but instead of continuing this way, when you moved the z, when you incremented the z beyond this point, it jumped out here and then came back, then jumped out here and went out again. So it's not necessarily going to follow the logic that you have in your mind, but nonetheless, it captures the structure of the data, right? And so here's an example of data from a sinusoid. And same thing, they have only 1 degree of variation, so the network structure is still the same. And you can see that the output of the network is basically the sinusoid itself within the training data. Outside the training data, of course, the behavior is not predictable. So what this means is that it's performing nonlinear component analysis, principal component analysis. It's learning the principal manifold of the data. Surprisingly enough, without being informed what the principal manifold was, without being given any structure to the principal manifold, you just give it the data, you learn the network. So long as you can guess the dimensionality of the manifold, it learns the manifold. So, which is kind of beautiful, right? So, and of course, when the hidden dimensionality is of a lower representation is of a lower dimensionality than the input, what we call a bottleneck, then this performs nonlinear PCA. It learns the manifold for the data, if properly trained. Of course, it's all if properly trained. Now, this has a very interesting side effect that we use in many applications of neural networks. A network that has been trained in this manner has a decoder, and the decoder can only generate data on the principal manifold. So what do I mean by this? If I look at this figure here, the decoder, if I just remove the encoder, and after having trained this network, if I chop this off, regardless of what input I gave to the decoder portion of the network, the output is going to be on the side, right? Or similarly over here, once I trained the network, if I eliminated the encoder, regardless of what output I gave over here, the output is going to be somewhere on this spiral. So the decoder only learns to generate data on the principal manifold. This is the behavior of an encoder. Everyone has heard of diffusion models and variational autoencoders. What's the difference between a diffusion model, a variational autoencoder, and a standard autoencoder? The only difference is that you actually learn the distribution of the data on the principal manifold. The autoencoder itself will learn the manifold just fine, right? So, which means that the decoder represents a source-specific generative dictionary. If I trained an autoencoder on digits, and then I threw away the encoder and just retained the decoder, regardless of how I excited it, the output is going to look like a digit, because that's what it's learned to reconstruct. It's learned the structure of the manifold, the space in which digits lie, and it can only generate data on that structure. Let's see if this works, but for this, my audio has to work. Okay, this was an autoencoder trained on spectrograms of saxophones. And then once we trained the network, we threw away the encoder and we gave it just random inputs to the decoder. So here's one example of what it generated. Here's a different one. It just sounds like a combination of saxophone notes being played. It's not garbage. It learned the structure of the manifold of sax sounds. And that's all it's able to generate. I can assure you that regardless of what input you give it, this is the kind of output it always generates. And if you try this on your laptop, it doesn't take a lot of effort. Or here is another example. This was trained on a clarinet. So again, it's learning the structure of the data, right? And it's only able to generate stuff in the space that's captured by the training data. And so I'm going to close this lecture off maybe a little early because you all look dopey and tired. But that may have nothing to do with the time. Okay. So with a cute example of how I can actually employ this. Signal separation, right? I'm given a mixed, again, these are all toy examples. You can implement this on your laptop in the next half hour or so and test it out and make sure that it works, right? So you're given a mixed sound of multiple sources. You want to separate out the sources. The standard approach, for example, somebody gives you a recording of someone singing and a guitar in the background. You want to separate the guitar, you want to separate the singing. How would you do it? So the standard dictionary-based approach is something like this. You learn a dictionary building blocks for each source. So for example, if you're separating guitars from drums, you'd learn a dictionary of guitar sounds, like all the notes of the guitar, from some examples of guitar recordings. And then you'd learn a separate dictionary of drum sounds, all the components that compose drum sounds. So anytime you pulled out something from this dictionary, it's going to sound like a drum. And now, when I'm given a mixed recording, our job becomes that of figuring out which components from the guitar dictionary and which components from the drum dictionary were combined to create this mixed sound. Once you can do that, then you can just reconstruct just the components that you pulled out from the guitar dictionary and you'd get the separated guitar sound. The same thing from the drum dictionary and you'd get the drum sound. Enough, right? And so in our case, so separation means you identify the combination of entries from both dictionaries that compose the mixed signal. And then the composition from the identified dictionary entries gives you the separated signals. Easy. We're going to do this with neural networks. For each source, I'm going to have a collection of recordings from just that source, and I train an autoencoder. And then once I train the autoencoder, I'm going to throw away the encoder portion of it, and I'm going to just retain the decoder. Now, the decoder I know can only generate sounds from that source, right? Because as I showed you, I trained a decoder from a autoencoder from a clarinet, the decoder can only make clarinet sounds. If I train an autoencoder from a saxophone, the decoder can only generate saxophone sounds. So here I've trained one autoencoder source and I retain only the decoder. And now this is a neural network. Here's what I'm going to do. The outputs of these two decoders are going to be added to give me my final sound. Then, now a neural network needs an input, right? Given any mixed sound, we are going to find the input to these two decoders. So these things are already learned and fixed. You're not going to be doing anything with these guys. Instead, given any mixed recording, you're going to find out how to excite this dictionary entry, this decoder, and how to excite this decoder so that when you sum their outputs, the output sounds like the mixed sound that you just heard. So to find the excitation I, once again, you can use backpropagation. Backpropagation is not just used to learn network parameters. Backpropagation can also be used to estimate the input itself because the gradients can be propagated all the way back to the input, right? So here you're going to use backprop to estimate the inputs. And then once you estimate the inputs, then I can just feed these inputs into this dictionary, and whatever comes out here is going to be source 1. This input goes into this dictionary, whatever comes out here is source 2. So let's see how that works. This was a one. So this is a 5-layer dictionary for each of the two sources, 600 units wide, very small. So 3,000 neurons, right? The idea is kind of cute, right? Again, I'm not claiming that this is the latest, greatest, and the state of the art in source separation. My point is that we're trying to illustrate what a network actually learns, and we are seeing what it actually learns. It learns the structure of the data. You can actually use it to recompose the data. Anyway, I'll stop right here. That's the a little bit early, but still, story for the day. Classification networks learn to predict a posteriori probabilities of classes. The network until the final layer is a feature extractor that converts the input data to be almost linearly separable. The final layer is a classifier that operates on linearly separable data. The overall training is a maximum likelihood estimator. And then neural networks can also be used to perform linear or nonlinear PCA, which can be used to compose constructive dictionaries for data, for instance. I'll stop here and take any questions.